Tady 1, 2, 2, raz, 2, raz, 2, 3, dobrý den, 1. Ne, jenom kdyby náhodou došly ty akumulátory. Já jsem sem dal akumulátory místo klasických baterií.
OK.
Je schováte do kapsy, ili mi je dáte, když tak.
Jo.
No, tady strany jsou. A dáte tam rychle tady ty baterky. Buď jedný, druhý, oni tam budou vydržet maximální hodinu. Jo, max. Tady by mohli vydržet celou dobu.
A je to teda nějak zapít?
Jo, v tuto chvíli je to...
Náš pedek to
tak vypnout. Jo?
Jenom ty nahoře.
Tam spíš akorát nevyhazovat tady to, protože oni jsou na věcí.
Jo, to mám. A já to tam podělí taky nejsem.
Nebo necháte na vrátnici.
Jo, to není problém.
Jo, nechat na vrátnici na moje jméno.
Tak dala někomu kolegu, aby vám to v pondělí do nás, ale nech tam dát.
Online, just use my computer just for. Well, if you connect to Zoom, then you can because now we have the Zoom. Okay. So you can connect your computer. Okay. And so that will be the end of share your screen. Okay. That's that. Okay. And the sound can be played from.
No, bude vlastně.
Jo.
To musí být akorát na spojené.
No, to je pravda.
Jinak to nepoběží.
I can speak without microphone. Problem is that if you will be speaking without microphone, then it will not take. Okay, then he will be my main star. Okay. So I agree with this. So he will be the only one speaker. Okay, yes. Because we don't have the second microphone. Yes, he will be on.
Can you send me the Zoom link? Or is it on the Discord?
It's on the Discord already.
Yeah, okay, then we will find it on the Discord.
Yeah.
Yeah. Can you show me on the Discord where is it?
And also you can verify point. Yeah, you can define goal.
Join, yeah.
Okay.
Let's
951
6484
depends on the
Discord.
on the large
Some update. 6484 48 42. Okay. Join.
And there will be a passcode, and the passcode is 548 715. And first start is
Recording in progress.
Okay. I'm completely muted.
yes, you are mute your speaker.
So I will. But I might have microphone muted.
Tenis.
Yeah.
1, 2. 1, 2, 2.
I think that they are still on the coffee break. Yeah. Stop the share.
Oh, okay.
So you can start screen sharing.
So I will just turn off Discord. Zoom
If you will leave the Discord, if there will be any questions.
Okay.
Mikrofon zase. 1.
But actually, it was relatively working from his computer, so maybe we can use this as a.
Okay, I'm
Nemám
sharing.
žádný mikrofon, který by mohl. A tady toto? Tak záleží, kde pan bude sedět.
You will be just sitting, right? Or you will be moving?
I will sit. Yeah.
If you will be all the time sitting, then we may.
Microphone.
Můžeme použít jeho mikrofon.
Jako jde to. Vy zaznamenáváte celý Zoom,
Ano.
to znamená, ten jeho mikrofon tam jde. Tam akorát,
It is very complicated workflow.
no jo, jenom že mu to tam bude chytat zpětnou vazbu zase z reproduktoru, aby to bylo slyšet. Takže když, no, záleží, kolik tady bude.
Step by step, then
Jo. Já jsem vám to nastavil. Já jsem to právě nastavil tak, aby bylo slyšet z reproduktoru a zároveň to. Ale v momentě, když pustíme tady mikrofon, tak nám to bude chytat zpětnou. Tam ten elektrotový já už neovlivním. Jo.
Okay, so let's try from the mic. Okay, perfect. So I have it.
okay, so now we will just have to wait a little since before the people will come.
No.
Oh.
Já se potom tady ne, tady ale tam akorát ten pán, co tady byl včera, že chtěl vlastně mikrofon, jenomže to nebylo zapojený, tak takhle.
They are starting to become. Yeah, first. I know. Very bad. I know.
Yeah, and yes, about the city. But next time I hope I cross my fingers.
Yeah, no. We used to have very much very when we were working on this okay. And also
Otherwise,
then I can use this as teaching material. I'm working on so in OpenEDX You know this platform? No, it's a free platform that is used in MIT and Stanford. Yeah. OpenEdX is platform. So this is the core of the people that will become. Mainly yes, or they just destroy. So we can start. Yeah. So this is the main part. Just because that's the only microphone you have.
Put it here and
No, you will take it. But that means that you reply when someone will ask you, then just repeat the question.
okay,
So it will be on.
okay. Thank you. So thank you, everybody. Welcome to this tutorial on chemoinformatics with Orange. Pavel, thank you for the invitation that we have this opportunity to present this. And we will delve into a little bit of basics of chemoinformatics and basics of visual programming. These tools are in fact not known that much in the community, but I'm you will also see the potential that this kind of tools offer. So first, I would invite the public to install the Orange software. The only prerequisite is that we need Linux system, because currently we use libraries underneath that work with Linux. Everybody please, just open the machines, and I have here Crtomir. He will help, he will go around your machines. So just create a virtual environment using VMV. So as simple as it can get, then just git clone this repo. And there you basically have the environment instructions where you can install them directly via pip install. So two things that you need is Python and pip, but fortunately with Linux machines you've got everything. So should I wait? Will you try to install it? Crtomir, will you maybe go around and... Yeah, I will. Yeah. And help, help here. Also there I see there is a laptop, and here in front. Yeah. So basically here the one advantage is that you basically do not need nothing fancy. Basically you need Python on the system and it just works. So it is basically lightweight environment. So introduction to Orange. Do you know some alternative visual programming tools? So some of you, maybe the older generation, know KNIME, maybe, and yeah, you know KNIME, of course, and Pipeline Pilot. Do you use, any of you are very familiar with KNIME? Okay, so then you will be also very familiar with Orange, right? So it is similar. So here is a workflow that basically you can construct it by your heart's intent. But here with Orange, it was developed in Faculty of Informatics in University of Ljubljana. It is open source software. It is very visual. So this visual constructing of workflows. It offers interactive analysis of your data. It is very versatile, so basically it is primarily placed for data mining. But here we are also trying to develop some widgets for chemoinformatics to maybe enable analysis in chemoinformatic field. It is very extensible, so the API is very nice in Python. So every one of you, I think, can write also your own nodes. And okay, I will invite you at the beginning. So me and Crtomir invite all of you to check that GitHub repo, fork it or analyze it, and also contribute, right, code to it if you feel so inclined. What is basically interesting with Orange is that it can really simplify quite complex tasks, right? So some tasks that include multiple algorithms can really be visualized in a simple manner, and quite intricate and delicate workflows can be constructed. And here, from these slides here, I would really maybe encourage you to check this article from Demshar, so the main author of this software, idea author, very nice article. And you can see here that the Orange is really in the literature. It is present, right? It is actively being used and actually to produce some good results. So you told me that you are versed in visual programming. So basically the premise is like this, right? You don't write any code except if you wish to make your or produce your own widgets. And you place a widget on some canvas, and each widget does a specific operation on the data. You connect the widgets via input pipes and output pipes, and you really transparently know what is your input data, what is your output data, and what operation is being done on the data by the widget, right? So these canvases actually can be quite complex. And what is for me interesting when I started working on this is that they can be really effectively shared. So, you know, when you share your code, if you don't comment your code, by the way, here I will do a plug for, right? Good code is commented code. So whenever you write code, comment it, please, abundantly. But still, in commented code, it is quite difficult when you get some piece of code from a colleague. You need to spend some time to analyze it, right? Well, with this kind of workflows, they come to us intuitively because we are visual, right? Our brain is very visual. And I found out that these workflows can really be effectively shared by multiple people and even worked on together without this initial input of towards understanding the workflow. So basically, how it goes. So we have some input data. We have some nodes to analyze this data to check what is going on. Then we can construct some models. We can evaluate those models, and then we can see the output on what we were trying to achieve. So I mentioned this interactive visualization. So nodes can, of course, visualize the data, like here. And in an interactive manner, you can always change the properties of your data visualization. So basically, what Orange is pushing you into is not just to have the data and blindly do some work on it or some transformation or whatever, but to play with the data, to explore the data and to get this intuitive feeling what your data actually tells you, right? So this interactive visualization is critical. So how is the platform constructed? So it is constructed from these Orange extensions that are like add-ons, right? That can perform various tasks, right? So you've got image analytics, networks, geo extensions, educational extensions, and we are trying to develop and are actively developing these chemoinformatics widgets that should really help you in chemoinformatics. Our main goal was educational role. to really elevate and really in an easy manner demonstrate these complex tasks that are being done on the data for the students, right? And for this task, this tool is amazing, right? So basically, on the left side, you will see you've got various extensions, and inside these extensions, you will be able to find those widgets or even nodes, right? In KNIME, they are often referred to as nodes, here as widgets. So here is our current collection. This is not as such. This is constantly evolving and changing because it is under active development by us. But what thing that I would really here emphasize is RDKit, is the library that we use a lot. And for everyone that is not intimately familiar with RDKit, I would really push you to this site, rdkit.org. It is an amazing gift to our community, I would say. So yeah, a good piece of code. So for Orange, go to this orangedataMining.com software. From there, check the YouTube channel. You've got a lot of study materials there, basically all possible topics. Then go to the blog. It's very interesting. They publish some subjects where they use this on, and check their Discord. This is the invite, and they are really they answer very quickly to anything that you could ask for, right? So yeah, here I would start with the tutorial. So first, one question: did you manage to install the Orange? Crtomir, will you go around a bit? Yeah, go around and try to. You try to install it. Okay. Okay. Nice. So we have there. You have it. Okay. Try. Crtomir, help them. And in the meantime, yeah. So Campbell, everybody, you know it, right? European Bioinformatics Institute, a wonderful database. I will not spend that much time on it. So first, let's go into the simplest possible case, right? So Campbell and how to fetch the data from the database. So usually the platform looks like this. And here we have those chemoinformatics widgets. And here, for example, just you drag and drop, right? You drag and drop the nodes. And now I will just copy. So this is HIV-1 protease, if you are interested. So I come from the field of medicinal chemistry and in silico design medicinal chemistry. So always I put a lot of emphasis into the biological context. And here I would also employ you to do the same. So always when you work with data of this kind, try to study as much as you can because this data is invaluable. And people before us already said that we stand on the shoulders of giants, and I also recommend you to do so because a lot of information has been deposited before us. And it should be used, right? So I often found that young people do not read or read too not enough, yeah, but I can employ from my experience, read. Okay, so here you've got, so we fetch the data. So immediately we've got this data loaded. So here, what can we do? So data info, we just check it. How many rows, columns, and let's immediately go to the data table when you can output this port from the Campbell fetch data and you check. So what we actually have here, right? So we've got a typical Campbell data set for this particular target entry, right? So P Campbell values, standardized, and some molecular descriptors are already calculated. Okay. So, question now from my side. Did you succeed? Does it work for you guys there? Does it work? Crtomir, can you go here also on the front row? I will go a bit on and then you can. Yeah, so first task, standardization of molecular structures. Yeah, so no strict convention is that defines how to represent the chemical structure. And this is one of the big hurdles in chemoinformatics, how to navigate all the formats. We were just talking with Pavel yesterday, how chemical formats are really a huge hurdle. So basically, we've got many problems, right? So tautomerization, ionization state, stereochemistry, then how aromatization is basically displayed. Are the structure calculized or no? So then specific groups like nitro here, right? It can be represented in many ways. And many forms, but basically this is the same compound, right? And here, this is one of the largest hurdles in chemoinformatics, really how to treat this deduplication and how to really deal with this kind of cases. So definitely what you want to do is check for uniqueness, right? And do we need this kind of duplicates in the database or no? Do we need to represent or standardize molecules or no? So this is a huge problem, and duplicates often more than not are present in a database that we use, and that is especially true for SMILES. And you should be really, really aware, because SMILES has many variants, isometric SMILES, right? Classical SMILES that can have multiple strings for the same structure, and then of course canonical SMILES, and so on and so on. So this is one of the tasks that we want to do. Because why? If we want to do structural searches, then we would get wrong or misleading results. And even if we model from this kind of databases, we can really get misleading results, right? So what we would like is some uniform representation of molecules, right? So here, what we can really do, here, again, we go to this chemoinformatics package, and you just drag and drop. And here you can see what can go on. So these are just classical faults. Metals are being disconnected if they are connected covalently. Molecules are being recharged, and you have to run it. So if you are familiar with RDKit, this is a typical RDKit workflow, right? Here it is, of course, present with a very nice node GUI where you can integrate it in your workflow. Okay, so here on the bottom you can see input data and output data, and here, of course, logs are being processed, so you know what has been done. So largest fragment has been preserved, or so on. So here, of course, we will go immediately into transform and check for uniqueness, and let's check for SMILES. And you can see immediately, if we go to the data table, you can see immediately this is our result, and you've got 570 molecules, right? So quite high percentage of duplicate molecules, right? Okay, so before we go on, did you succeed into any of these starting steps? You succeeded. What about you two in the back? You have it? Yes. All right. Okay. And there? Okay, try to if you can try to yeah, try to install it, because you will see from simple behaviors we can quickly build up. So yeah, okay. So we fetched some data from Campbell, right? Then we did some pre-processing, typical pre-processing for chemoinformatics. Then we want to calculate some fingerprints and maybe present this data, right? So okay. The same set as before, HIV-1 protease. This is also a personal choice because I work with antiviral compounds, and a lot of work has been done on HIV, and also historically computational methods have been used for this kind of research. That's why it is close to my heart. So aspartate protease, a key target, and we will do TSNE, so T-distributed stochastic neighbor embedding, where we can really predict the probabilities of 2 points in multidimensional space and plot it or reduce it to, let's say, 2 dimensions. And it works something like this. And what can we do, right? So I don't know why I'm on this. So yes. Okay, so we will go like this. We will just do in parallel. I won't even change the workflow, and we will just go fingerprints. Yeah, immediately they are calculated. So RD-kit fingerprint. And now we will go data merge. Why do we want to do data merge? Because it is designed in this manner. If we check here, the data table, we've got here just input data. In the future, we will also change this so you can choose whether you keep all the original data or not, and you can see bit decomposed fingerprint, right? So yeah, 1024 bits, right, for this fingerprint, and I will merge it. Why? Because I want to also keep the original data. You will see why. And yeah, we will just merge it by index. Yeah, and you can immediately check what is going on. So here, each node, when you check it, you can see here what is the input and what is the output data flow. And you can immediately check what is going on with the table, right? Yeah. And then we will go to TSNE, dimensionality reduction. So here you can see it. The dimensionality reduction being done, and you can of course apply PCA pre-processing or no, how to you initialize or normalize the data. It's completely depends. So you can play with this data right here. Let's say a selection. I told you before that you can play with this data, right? So here you can see that I selected this part here, and we've got 24 molecules, right? So here, if we check, we go here, we've got this molecule viewer. And here we can check. So immediately can see this subset, right? How we can play with this. So it is really, really intuitive. Okay, so yeah, basically a typical workflow, some data entry, you inspect what is going on with your data, you view your molecules. Then you do some pre-processing. Here we just did for uniqueness. And then you again check what is going on. Then you calculate some fingerprints, merge the data, and then you can do some visualization of the data, right? So these 2D dimensionality reduction techniques are really, really powerful, right? Probably many of you are used to do principal component analysis and then plotting two principal components, but there are many, many more. Some preserve the global structure of the data, some preserve more local structure, so you should really be careful about this. But yeah, it doesn't matter. So, okay. So if we can immediately see that that we grouped and immediately clustered in a way these compounds together. But of course, this is just the dimensionality reduction technique. If you wanted to cluster, you would need to do some of the clustering techniques that are on top. We will not dive into there now. So, okay, I have a question for you. So did you succeed? Did you were you able to do back there? Yeah, what about you? Did you? Yeah, Crtomir, go help on the right side. Yeah. The data set is here. It's written on the yeah. So just use Campbell activity, right? And fetch the data set. If you just paste the number, of course it will not. Yeah. Yeah, it is this Campbell 2366517. They are succeeding. Nice. Did you succeed in the back? Okay. So here we can also do, let's say, some hierarchical clustering as one introduction to the clustering view. We will use maybe not fingerprints, we will use max structural keys. So basically they are defined, they are a dictionary of smarts patterns that are found, right? Or not in your molecule. They are predefined, that's why they are structural keys. They are distinct from fingerprints that are generated on the fly, right? Usually based on some path, if we talk about Morgan fingerprints. So they are basically fixed-length binary fingerprints that represent predefined molecular substructure. And you can really find them, and they are very nice for quick comparison, quick searches. They are really rapid to calculate. And you can also modify and play with them yourself. So, okay. So here we will again change our approach, and we will just go max generator, and they are already processed. Yeah, and we can already see here. So this is one quirk of orange. So you have to, because we will do Jacquard or Tanimoto similarity, you have to define here that it is a binary. So we will just go here, max, and we will go type categorical apply. And you will find distance. And we can immediately calculate the distance matrix. Yeah, ignoring non-binary Jaccard index, very nice. And then we can go into the distance matrix. And here it is. So all against all, distance matrix with the Tanimoto similarity, right? We will go also into the distance map. One variant, and you can immediately see it looks like this. So this is how clustering would go. You can order it, you can define the range if you're interested in specific splits, right? Annotate it or not. And again, you can do here hierarchical clustering. And you can again see, okay, you can see the cluster representatives. And again, I told we can play with this data, right? So this is really pedagogical tool. If you want to show the audience what is going on, this is an easy way how to do it. And also, if you want to play to get this intuitive feeling for your data, you can really do this, right? In an easy manner. So select, and here, immediately whatever I select, I've got an output for, right? And we can immediately do data table. Of course, we can output, save the results, or whatever we wish. So here it is. Or we can do even, we go with our own and we go molecular viewer. And see, yeah. So this is a cluster I selected. It was one of the, and we can see that it works quite well. And the key here is really what I would really emphasize: explore and play with your data. Explore it, yeah. How does it change? What are you trying to do, right? This is imperative. Okay, so let's stop a bit. Did you succeed? Yeah. So the one tricky part is this domain change, right? So you have to define the categorical values there. Did you succeed? Yeah. Yeah. Should I show you again? Yeah. So when you do the distances, you've got basically this is tailored for data wrangling and basically data mining. You've got many possibilities. Sometimes you really have to play with this a bit, so you tailor to your chemoinformatics workflow what you're trying to do. Okay, one typical example, very nice for the students: drug filtering, Lipinski rule of 5. So I always ask the audience to describe to me why do we use Lipinski rule of 5? Yeah. 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 And this is a typical answer that I get. Lipinski, druggable molecules and drug-like molecules. Lipinski has nothing to do with druggable and drug-like molecules. It is only, it was designed for bioavailability pairs, right? Oral bioavailability. But we've got, this is a typical misconception, and I really like to clear this up. But basically in chemoinformatics, you've got many filters, right? Early data processing is imperative. I employ everybody, my also students, I always see them just using some data sets blindly without pre-processing, without looking at the data itself. in this conference, we see constantly a lot of very intricate, delicate protocols and methodologies that are really dependent on the input data, especially here, a colleague that was describing AI methodology in de novo design and so on and so on. So these protocols, if you listen to the lecture, are very delicate and intricate, right? So have this premise in your mind: garbage in, garbage out, right? So have good data, work with experimentalists, use experimental data constantly as much as you can. This is imperative for quality of your work. Okay, so typical Lipinski. Again, we can just use the filters and check what's going on. And here in our workflow, we have this. For example, I will just start here from the beginning. So here we've got 690 records. And then we've got various filters implemented, of course, within criteria, and then we try to filter it. And here, if we go then and typical data table, you can see 362 molecules are being within criteria, right? So how is this possible? If we have Campbell data set, half of the molecules are filtered off. Yeah. Yeah, how is this possible? Half of the molecules are filtered off. Yeah. So bioactivity data has nothing to do with Lipinski and oral bioavailability, right? So this is Campbell, that is a collection of biologically active molecules, right? So that is completely another goal that we are trying to achieve. For example, with Lipinski filter, right? Okay. So this is an exercise for you who are working on the machine. So cluster the compounds with hierarchical clustering, but now try to use Morgan fingerprints instead of max structural keys, right? So Morgan fingerprints, radius free, for example, and then fingerprint is generated on the fly based on the radius, right? So fragments that are found are then written in your fingerprint bit string. So yeah, please try to do it and tell me, was it difficult and did you succeed into doing it? So here we used fingerprint calculator, and here is maxed. It's the same, basically just exchange the fingerprint. Oh, sorry. Okay. So from the data, what do we do? Again, just fingerprint. Immediately, Morgan, compute, check, do we have them? Always do data table, data checking, always. How does it look like? Yes. Edit domain. Sorry. trackpad. Again, Morgan. Type, categorical, apply. Then we go distance. Jacquard, and we're here. Let's say distance matrix. Yes. And we are here. So it was easy as that, right? So here, really think about this, right? What did you use here for clustering? What can we use, right? We are basically in chemoinformatics, we are navigating chemical space, right? If we want to easily navigate physicochemical descriptor space, what do? We generate what? Physicochemical descriptors, right? And we use those for or dimensionality reduction, PCA analysis, or whatever additional method, and then we can do various clusterings, and we will plot physicochemical space. Here we did clustering based on Morgan fingerprints, right? So we did structural chemical space, right? So is this structural chemical space the same if we use some other descriptor or maybe even max fingerprints? What do you think? It's never the same, right? It can be similar, and your task is to identify this similarity islands and cliffs and so on, and your task is also to identify where are the differences, and maybe those edge cases are the most interesting and the most important, right? Okay, did you succeed? In the back, so just exchange, right? The max keys, just exchange them for Morgan fingerprints, and everything else keep the same. So do the domain edit, select bits, and yeah, change the domain to categorical value, and then just do distances and calculate Jacquard index all against all, right? Here in the front row, did you succeed? Very nice. Okay. So here we also have another interesting case. So we've got a data set of alcohols with their boiling points, right? And we will try to generate a linear model, right? So here, I have it prepared. So it looks like this, right? Again, very, very, very simple. So here we've got alcohol data CSV file that Crtomir uploaded to the Discord. And basically what this is, you see it's smiles of various alcohols and their boiling points, right? That is really an eclatant pedagogical case, right? And then we calculate more descriptors. You see this small set of descriptors. Here, by the way, you've got a lot to choose from, so really play a bit. You can find everything that you need most of the time. But here, interestingly, we'll just calculate this simple set of descriptors, right? And then, of course, we merge the data, and the data looks like this, right? So we've got smiles, we've got calculated descriptors, and we've got this boiling points, vrelišća, we say. That's why it is TV. Okay. Then we select columns. And you can see we use these descriptors, and the target value is this TV, right? Meta is only these smiles here. This is the metadata, right? Yeah. Just, Pavel, would you just, okay, it's okay. It's not, the machine is not powered, I think, but it's okay. I think we will find somehow. I will change it, but let me first explain this to the end. So yeah, we select columns, and here what we are interestingly is TV, right? So this boiling point temperature, it's a target value. And then we can use this node, this is test and score node. If we check it, we can do and compare various models, right? So I use linear regression or random forest, right? You can use whatever models you have here. I will just show you. So these are the default really models that are really commonly used, and just use a model, and immediately it gets recalculated, and you can check, yes, here R square value you can see 0.95, right? If yeah, it looks like this. So yeah, this is the boiling point, and this is the predicted boiling point, and you can really see how this trivial task is achieved very, very elegantly, right? Again, if you just select a couple of molecules, what's going on with them, you can do them you can see the molecular viewer, this subset. Now let me just check what's going on here. So did you succeed in the modeling? Did you produce the linear model? Yes, now it works. In the first row, did you succeed? Yeah? Okay, perfect. And of course, if you use other models, right? You can immediately compare them, right? What is their performance, right? Here, I want to emphasize one critical thing, right? This data intuition, that you know what you're doing, is critical for effective modeling. And more often than not, I meet cases where people use neural nets, but they don't know what a linear model is. So more often than not, simpler models perform better, much better. So really, really study the data, what you have, right? And here, in this eclatant case, we can see that linear model actually performs really nice for this pedagogical case. Yeah, I solved the powered problem. Some do not work, but okay. And okay, an intricate workflow, and maybe for the last, let me show you just a simple classification model. So this is DNA gyrase dataset. So if you wish to repeat it, please again fetch the Campbell node and just write this number. It's different than the previous, right? And then fetch the data is the similar data set. And again, looks something like this, right? It is just expanded previous workflow. But what we did here, right? So structures, and we've got Morgan fingerprints calculated again, right? What we did here is we use this discretized node just to pedagogically show, and we just divided compounds into active and inactive based on P. Campbell value, right? Then I use always this data sampler node where we sampled some data and left some data out. Why? Because I always advocate the usage of these holdout sets. We always hear about test and training set. We rarely hear about validation set, and even more rarely hear about holdout set. So always use it in your work. Okay, that doesn't matter. So we go on. So we've got this data table, and then we again select the column. And we use Morgan fingerprints, and target value is P. Campbell value, that is categorical value, right? Active or inactive. And then again, we've got test and score, and we've got two models, again, random forest and gradient boosting. It is not XGBoost, it is implementation of scikit-learn. And if we can check, right, how it performs. So these are the results, and you can see the precision, gradient boosting, and of course random forest. And amazingly, for such a simple data set, right, only a few hundred compounds with simple descriptor, you can get these kind of results. And again, you also immediately see the confusion matrix. You can explore the results, select correct, and immediately we've got the values that are correctly predicted, check the data, what is going on, and at the end, you can also do the TSNE on the calculated data. For me, interesting is that we colored by this P. Campbell by random forest, and the shape is P. Campbell value, and you can immediately see how good this model is in classification, right? But you can immediately also appreciate the complexity of chemical data that we have at hand, right? So one-off clusterings and immediate conclusions are never available in our research. So you can, of course, appreciate the method works good, but the chemical space is a little more difficult to describe than this. So with this, I see I'm out of time. I will conclude. I really thank you for your kind attention, and I would please ask you to also fill up the questionnaire that Chert will tell you where to get it. And thank you for your presence and attention. And do you have any questions? I'm open for questions. Yes. Yes, so basically direct conversion of the nodes is not possible, right? Because all in all, it is a bit different under the hood, right? But it is very easy to convert, to convert between the two. Because the analogy is quite high, you can really do similar things, while this option being more lightweight, much faster, quicker, and more interactive. But yeah, both are an excellent tools, and I think you can convert between the two but not automatically, right? You have to reconstruct the workflows, but it can be done very easily. Yeah. Yeah. Yeah, there is. In the Orange data mining, they have a huge repository of already working workflows, but they are tailored towards data wrangling, data mining, big data analysis. Me and Chert are working towards doing this, and once we have, we have plans that after this will be more mature, we will definitely, because this will hopefully be part of the Orange, and we will of course start to include also the workflows there. But we are also, we are active in all communities, and we are really advocates in this visual programming also via KNIME. KNIME is excellent tool, and really it's a game changer by my experience, right? In the researchers and how they perceive data. Yeah. Yeah, it actually is, and it actually quite excellent support. Yeah, you will, if you start to dig there, you will find amazing stuff. Yeah. Yes, it can. It has an API, and it can run elegantly. Yeah. Yes. Yeah. Okay, thank you. Okay. Pavel, the power outlets down there do not work, but these ones do. And in the middle of the meeting, your computer is dying or red flashing. How come it is plugged in? Oh my God. Yeah. Thank you. Yeah.
It's not very well.
Yeah.
Better than mine, but you are much more small than me.
I will tell you honestly, Orange were much earlier before. KNIME didn't even exist when this was deployed, but because KNIME didn't exist when this was developed.
Really?
Yes, but we are Slovenia, nobody knows them.
Yeah.
You know, that's the key. But otherwise, KNIME is more mature, definitely. It is also meant for
companies,
business,
big
yes,
business,
big
yeah.
business, also suitable for large tasks, but still you can get it even better. We do it also more. I don't know, whatever. Yeah, otherwise I'm also an advocate of KNIME from their beginning. And obviously,
Fingerprints, then all one point then you need to fuse data from original level, but here is all this. Oh, but that's okay. This is all the job. Yeah, but if we do one million instead of 3, yeah, this simplified it. Yeah, the visual.
But actually, I'm proponent of many widgets of simple tasks, because then everything is more transparent and the students understand it easier. For me, when the student builds a workflow, he really gets it, what is going on, and that is the biggest advantage. And even to show it to it is so easy to show what is going on if you change something or did this or did that. And with this, for the first time, students really, what I observed is they really know what they are doing, not some abstract numbers. Okay.
It's not massive, but because maybe two bring dust. Everything started from the first steps. It's normal.
Hello, Igor. Can you hear me? Hello? Hello, hello, hello. We still have time because the previous session ended a little bit later, so it's nothing really serious, just to be sure that you can hear me. Ah. Hello.
Hi, Carol. Yeah, I can hear you.
Hi. I'll try to make myself more visible.
Good here. Yeah, I can see you.
Ah.
Okay, but no problem. So we should connect in 10 minutes, 5 minutes, or
Yeah, basically you can start streaming, start sharing your screen.
yeah, but we'll do later. No problem. Just let me know once people will be ready, and yeah.
Yeah, well, currently there is nobody instead of me, so you have time.
No problem. Okay, I can try to share just to see.
Yeah, just to see whether it's
works,
working.
yeah.
Oh, and we have the first participant.
Great. Okay. So, can you see? Yeah.
Yes. Yeah, we can.
Okay. Excellent. 1 second.
Hey. Yes, Igor is already online, so. Yeah. Unmute us so he can hear us. And he's looking there. Hello, Igor.
Yeah, hello. Nice to see you.
So the people start to come. So I think we can wait few minutes still, so you can chat with the guys here. Huh? Oh, so they're so in the middle of the lecture, computer is dying. Oh, cool. Those guys. Uh-huh. So currently we have 5 people in the audience, so I think we can wait, let's say 2 minutes, 2 more minutes, so they can come from the lunch. The important part about lunch is here is that they are made by in a bistro by a guy who was working in a Michelin restaurants over the world, and now he made a bistro. So it's a really good quality food, and it's relatively quick. But as it is so good, it usually slows the people down.
You really put a good motivation to come next time. You see,
That
definitely
was my
next time-
intention as well. That's true.
Unfortunately, I was not able to join this time because I have overlapping meetings and I'm now in Milano.
Oh,
That's why
I
a
see.
little bit. Yeah.
Well, I suppose that the food in Milano is so you are not
Yes.
on the other side.
Yes, that's true. We have been in an excellent restaurant yesterday.
Okay. Guzel,
Yeah.
can I ask you that you will be sitting here and responding to Igor because I will have to leave?
Okay.
Yeah. And basically to have a Discord if there will be some questions on him from Discord as well. So it has to be read to the mic. Okay, so I think that you can basically start with screening your with sharing your screen. Everything should be running, so you can start.
Okay, just a second. So let me just. Okay, so hello everybody. I think you see my slides. I will make now full screen. Okay. Okay. So it's my pleasure to be here, and thank you very much for invitation to present during this school. Unfortunately, I'm not in person because I'm now in Milano, and unfortunately, it was not possible to come just for one day. That would be just not possible. I would be still flying. So what I will be speaking today, it's about OCHEM platform. I will give some overview, and since we have 2 hours, I will also try to show how to develop models with this system, and you may also try to do it online or later on. And also I have sent to Pavel PDF file of tutorial, which I will not really follow, but you can use it to learn about OCHEM offline. So what is OCHEM? It's a platform which was developed in our institution. Is ready for online since a while, and yeah, this will be chapters will present. After this, I will be switching to the online from the online presentation to OCHEM itself. And why this platform came to mind? Because yeah, we are in drug discovery field, and the drug discovery field, at least traditional process, takes a lot of time and has a lot of steps, and some of these steps can lead to failure of chemical compounds. So what here's issue is basically once you found some compounds by screen, by target discovery validation, you go to lead discovery. After this lead optimization, admit in DPK, and here compound can fail because maybe it's not soluble enough, or it has some poor DPK properties, or it's not as stable, and so on. So people can invest a lot of time, like 4 years, to find lead compounds, and after this it just drops because of poor admetox properties. It can be even worse. It can go further optimization, profiling. It can fail also there. Maybe again solubility problem. You can't make this compound soluble enough for application as oral drugs, and that's again bad. Or even can fail later during clinics. Maybe there is some toxicity issues which you didn't discover during the previous phase, and admit predictions can help, however, to less degree, because already for the latest step, in vitro assays and in vivo testing is done already in animals, and it should provide better translation to the clinical research. So preclinical research, clinical research, which are most important, and people are trying to find a way how to avoid failure of chemical compounds on the later stages. And yeah, so profiling basically in virtual chemical space, sometimes during target discovery, which could be also computational one, and finding the most promising candidates with the most favorable properties can help you to avoid problems on the later stage of drug discovery. And what are the admetox properties? Why they are important? Because very simply, drug, which usually it's given orally, nobody would like to get an injection, has to go from many stages, from stomach, intestine, liver, blood, can be digested and extracted by kidney. And during all these steps, chemical compounds can lose activity because it, for example, will be just a liver will be metabolized and it will be not anymore available. So if you can predict some negative effects, would be great. Some of these effects they're not necessarily negative. For example, without metabolization, chemical compounds stay in the body for life. So we need some metabolization, we need some excretion, but it should be within some limits. So basically, optimization of net properties, it's you have some windows and you would like to have your compounds within these limits. So not very much metabolized fast, not very much binding to protein albumin, but sufficiently to be active. So this can be done during the later stage of drug discovery, but if you can predict these properties in advance, you can possibly simplify life during this clinical and profiling of chemical powder stages. So they could be much faster and more efficient. And this is how it's done. So Admetox properties are optimized during this space, during lead optimization, lead profiling, but prediction of them and finding compounds with good properties, which are likely to be optimized well during later phases, are essential. And the idea that if you find compounds which are very likely to be failing because maybe they are non-soluble, maybe they are toxic, you can see some toxic groups there which are likely to create problem later. You can just skip this compound and early you do this, better will be results. I would say that this ideology changed now. People are thinking that maybe we should not pay too much attention to these properties. We can optimize them later, but completely ignoring them, it's bad because you really can get in trouble with optimizations during the further stages. And companies like Bayer, this is an example where they published, explain what they have done. They developed a number of filters, and you can see that during latest 15 years, unfortunately, they published already 6 years ago. We don't know what is now there, but there is quite a lot of development in the field. Like in 2005, they had only few models, computational models, which can predict compounds. And later on, they added new models, they added new algorithms, they added new methods, and more models become of green color. These are robust models which can be used very well to predict chemical compounds, their properties. And I think now many more models will appear based on graph neural networks, based on NLP, natural language processing methods like SMILES and so on. So I think this is picture is dynamical one, new methods appears, new models appear. Would be nice to see what they do now. So idea of OCHEM was to make such tools publicly available, but for academy, because of course development in companies, they are using data from companies, they are not available to outside of company. So when we started OCHEM, it was already quite a while ago, we had the idea to create a public platform which will be accessible to everybody, where people can develop model, but they also can publish model. So that's an important part of OCHEM. Once you develop model, you can publish model, and this model will stay in OCHEM for as long as this platform will be working, and you can apply this model as it was published in literature. That was motivation to make models which can be applicable to new compounds, which can be published in journals. You can refer to these models, and this model will be staying for a long time. So just use this when you need. So the central part of OCHEM are still not models, but data, because models as good as data. So if you don't have good data, we don't have a lot of data, we don't have quality control of data, we can hardly develop new models because we have this trash in, trash out. So we should really take care about data, and that's why OCHEM was putting a lot of attention to have good annotated data in the platform. So this is how OCHEM stores each data point. Data points are records. So we have article, we have property, and in order to provide reliable information to the model developers, we store as much as possible information about this record, about the molecule. So what do we store? To restore, of course, we store a molecule. Molecule usually provided like SMILES, SDF files, MOL2 files, and in order to be stored in OCHEM, they are converted to the same representations internally by applying some standardization. So we use Kekulé representation. This avoids problem for aromaticity, since different algorithms can use different aromaticity. And we just do Kekulé representation, and when you upload data, they will be converted to this presentation. If it's not possible, you will see molecule will be shown as error. In addition to this, we store names. Again, frequently in articles, people provide not only structure, but also names. And in theory, these names should match chemical structure. In practice, it's not always. Sometimes there is mistake, can be in structure, can be in name. And if it's not the case, name will be highlighted with a red color. Or maybe it's not found in database. Names are checked against PubChem to verify that by searching PubChem, we'll get the same compound. If you get the same compound, okay, name is validated, it's green. If you don't get, it could be also red name, or it could be a blue name. It depends on the stage of PubChem. Sometimes PubChem give errors and we can't validate. But if everything okay, you see green names here. Of course, we store properties itself, what we are predicting, and properties, there are many of them in OCHEM, probably too many that should be there because there are some duplicates. And while we tried to avoid duplicates, that was not the case in the beginning. So we have, I don't know, 600 properties which were introduced by different people. And what is important here, property has some description. So I will, after this presentation, we'll go to them. Okay. And once you click on the property, you can see what does it mean, this property. But sometimes by abbreviation, you don't really understand what this property. Here, for example, it's toxicity of chemical compounds in water. So you don't understand what that means, this log IGC50 -1. Importantly, property comes together with new conditions. When some properties really doesn't make sense without condition, like for example, boiling point, it's not determined without condition, without pressure. So this property should be provided to be stored in OCHEM, and this is called obligatory properties. But sometimes we have like non-obligatory properties, like for example, somebody would like to add some comment about compound or provide some additional, not related, completely obligatory property. They can be also stored. So here, properties can be added as many as you want, and this allows, for example, to group chemical compounds or maybe to look that the data are not reliable and so on. So that's kind of features which is very nice in OCHEM. You can provide rich description of each molecule. Also, very unique and very important feature of OCHEM, we store units as they were published in the article. OCHEM has a very powerful tool to interconvert units within system of unit. So, for example, if you are using concentration-based measurements and properties, the unit should be concentration. You can provide its nanomole, you can provide like a millimole per liter or milligram per liter or log milligram per liter, whatever. It doesn't matter. OCHEM will convert them to the same unit when you will make model development. And it will also show properties in the same units, default units, when you see them in database. So this is really a unique feature. And we always say people, please don't try to convert units to other same units, for example, for your modeling. It will be done by the OCHEM if you are using this. Even if you export your data, units can be the same as you need. Advantage to provide units as they are published is to track a record. So imagine you have, for example, here a nanomole and concentration and compound was wrong. Simply somebody introduced wrong compound. And if you convert this to log milligram per liter, for example, it will stay wrong, whatever. And after this, you may find mistake. You correct compound. Now it's correct compound, but it's lost because you already converted to milligram per liter, and this wrong value will stay in the database. But if you use a published unit, when you convert compound to the correct one, you have correct measurements, you have correct data. So that's why important. Don't try to make more work, which is conversion to some standard units. Just use molecules with properties with the units as they were published. This is the best. Of course, we have source information. So each record in OCHEM comes with article because we would like to know where data come from. We don't need a data which comes from nowhere where there is no description. And if you upload data without indication article, they will be stated as unpublished data of user and your name. So, but this way we see that, okay, somebody tried with some property, just upload to maybe play, and we don't know where it comes from, but at least we know the user who introduced this data and so on. But most of data in OCHEM, which are publicly available, are with an article or book. And if you will try to publish data which do not have correct information, you will be not allowed. So now we just forbidden to publish data which like hidden data internal for some projects, because just pollute. We don't need data which like some file and they were put from these files. Nobody can use this data except the user. So why in this case this data should be available to everybody else? So basically, I would say that to correctly upload data to OCHEM, you need to make some small efforts, but it's required because the data can be reused by you, by other users later on. Also, we know who uploaded data. Always there is information who uploaded data, and the users of same type, of same category, because we have users just beginners who just make account and start to use, or we have validated users who already were working with OCHEM for a while. So it's also possible to request myself to validate user. So it's called validated users. They have higher priority, and you can edit data of other users of the same priority. And still, we would like to know what was changed, who did this change. That's why we have two people. One is introducer, another modifier, and basically also the introducer can see that his data, her data were modified by somebody and can also look what is problem there. Usually, we didn't see that somebody was trying to destroy data. Sometimes it can happen by mistake. People dump some corrections, wrong one, but this allows us to see what is going there. So this is basically OCHEM schema, and let me now show OCHEM itself. So I will just share now Firefox. So this is basically OCHEM, the platform that we have developed, and it's publicly available. And I just close. And you can go to this website, and in order to use OCHEM, you have to register account. You can also go as as a guest user, but there was some type of hacking of OCHEM, and the website was already all the time down because some person tried to download all data from OCHEM using HTTP request. It's made very slow, so I just disabled this anonymous access. And but if you create account, you can see all data there. So how to create account? It's very easy, and maybe I will again enable this again later. But it's like for the moment it's not possible until I will solve the problem with people trying to download all data, but like page by page, which doesn't make sense. So you can create login. You can create password, and you can register a new user. I will do it for myself because I just would like to be completely new. So let's Tetko new, for example, just to show how it will be working. And you provide email, so now cool. You can do it yourself if you have not done this. Right. Yeah, last name required. Organization, it's academic, and that's all. So basically, no. Okay. So you have to accept last agreement, which was put by our center. Idea was that center would just like to declare that there is no responsibility if something is going wrong with models or data which you have downloaded from OCHEM, which makes sense. I create account, and I should be working. Yes, no, password not much. Okay. The problem is not clipboard. So once you have done account, you can log into OCHEM. And here we have properties, conditions, and so on. So here we are. Tetko new, and you can do the same. You can create your account, and here we have compound properties. We have properties, yeah, itself. What type of properties we have? We have baskets. We have yeah, different units. And if you go to properties, it will take some time because it's old system. When we developed originally this OCHEM website, it was more than 10 years ago, and at that time we had 100,000 properties max. Now we have 5 million. So it's a lot. And even I put a server on a very fast platform, it takes some time to just index all data. Here's an example of one of record. And you can see that for this record, we have a lot of conditions. We have pH, we have temperature, method, and so on. For some others, it's not provided. And this really depends on the user. So, for example, here it was a colleague of mine. She was introduced this data from a different publication, and this information was provided there. She introduced everything. And here, for example, myself, I was not caring too much. I didn't introduce all this information because it's additional work. So you can have different records with different degree of annotation. And that's, of course, best to put everything, but sometimes you don't have so much time to do this. And if you see this record, we have molecule, we have property, we have units, we have reference, we have information in the article, on which page it was published, and so on. So it's possible to add information. It's not so much time. And if you get to analyze data later, it could be quite helpful to find what is, for example, wrong with the data. And here also what is important, sometimes you see this green button. This is also one of the properties which you can indicate when you upload data. And this says that these data were measured in this article. So basically, you can have different type of data, measured article or benchmark data, where people were collecting data from many articles and doing some analysis. Of course, the data which were measured in that are the most valuable one, because you can go to the article, you can really look for the article, and there is some mistake, you can understand why there's mistake. Data which collection other data points, they don't have information. So we have this button, which basically can be provided on different steps. You can, when you upload, you can provide information, but also when you edit data, you can provide information. Okay, that's basically I want to show. And properties, let's look for properties. We have many properties, and for example, you see we have 700 properties. I think I have total hidden properties, maybe 5,000. It's quite a big number. So, but most of properties are hidden because a user will get to develop some models, and maybe they don't spend a lot of time to search for existing properties. Just let's make a new one. Okay, no problem. But once you publish model, I will check whether this property already exists. If yes, I will ask to change to this property. Here, example of property which, like log P, we don't have any obligatory units, conditions, and property like log D. It does help because log D should be defined at some pH. So we have obligatory condition, pH. And if you upload data without pH, OCHEM will say an error in data because it doesn't know pH, and log D without pH doesn't make sense. And for log P, for example, if you look here, it doesn't have this. I'm just upload, and also can see here that different people still provided, for example, for log D, different information like buffer, some comment, method, phase analysis, and so it's possible to add any type of condition which you think that they will be useful for you. Now looking for log P, okay, it's there is no this obligatory condition. So if you upload log P value, which is supposed to be measurement of autonomous water partition coefficient, and then for neutral compounds, pH should be determined by this neutrality compound. It doesn't need to provide it. But still, some people can provide pH. For example, you see some people provide this pH because they want to state this, even if they know this compound was neutral with pH. So it's possible, but it's not obligatory. Okay, and we have different properties. You can always look, for example, like stability. This is my problem. Sometimes two times press the same button. You see plasma stability, for example, you have metabolic stability, you have liver microsomal stability. So there are different units, there are different properties that measure different units. For example, liver microsomal stability can be measured by half time, it can be measured like percentage, so a percentage of degradation at some time. It can be also measured like yes or no. It's depends on the article. So we allow different representation. However, basically these are related properties, but we give this flexibility. So somebody would like to work with classification data. Okay, you can do like this, or you can maybe join them and so on. So OCHEM really allows to define different ways, and really, if something is missing, you can add it quite easily. And yeah, that's basically what we also have there. We have conditions. So conditions defined here. You can add new condition, and if you do this, you can put name. You can select units, default units, and provide some description that people can understand what you have done. What we have also, we have units. Units. Something which relate to system units. For example, we have like speed, for example, for CACO2. It's a permission from membrane. We have different units. Again, as is published, used. And for example, pressure, we have also different units, atmosphere, bar, and so on. Kilopascal, hectopascal, HPA, hectopascal, so on. So basically, again, as data were published, they should be uploaded. Okay, I think this just like to show you about data. Let's see, data is the most important. Data, not models. Models you can calculate, but data is difficult. Now I will go back to the presentation. We'll share slide here. So here, as I showed about this, and we can go to the next slide. Okay, of course, it's not only database of properties, but also model environment. And over years, we were adding some different methods, which we believe the most powerful one. And soon we will add 2 more methods at least as a result of AdMetox challenge, which was running on the web recently. I see that there are some methods which are very powerful, but not yet on OCHEM. But idea was just to select whatever available is literature, best approaches, methods, best descriptors, and provide user quite easy workflow where people can upload data or use what is available in OCHEM, select descriptor, representation molecules, build model, and validate them. So this was main idea, or one of the main ideas: collect data, develop models, which in principle should allow people to easily develop models. And here I show step: you select data, select descriptors, build model, and validate. And after this, you can publish this model. You can try to predict new compounds. And if you publish this model, it will stay online as long as OCHEM is alive. We have models developed in 2011. They are still working and can be still applied to new data. So next one, and for descriptor calculation, we use different presentations depending on the program which will calculate descriptors. So we have 1D, 2D, 3D descriptors, and all of them can be applied with different types of models. Example of descriptors which are calculated by just one program, AlvaDesk. It's 6,000, almost 6,000, 5,600. And depending on the need, the user can select all of them or can select only specific descriptors. If, for example, there is some knowledge on which descriptor will work best, this descriptor can be selected and they can be used for modeling. And should be mentioned, AlvaDesk is a commercial program which is available from a company, but we have a license and permission to use AlvaDesk in OCHEM for what we are very grateful for the company who developed and support the software. And apart from this type of descriptor, we have many more. So I will switch to this after this to the OCHEM, but just to show that we have different type of descriptors like multi2, CDD, GPLP, which were published in respective articles and were added to OCHEM to be used for model development. Again, we usually test the descriptors, they don't work at all. We just remove them because we don't want to pollute OCHEM with something that does not work. But those which are working well are here. So Sinus, for example, descriptors were developed by Pavel Polishuk, and again, thanks to him, we have them in OCHEM. In addition to descriptors, you can use predicted properties. So this could be also added as descriptors. If you would like to use a model where log P is important, you can just use prediction of this program, log PS, for example, and sorry, should be not so fast. And you can have lipophilistis descriptor, which will be calculated for your model development, but also for model application. Also, we have 3D descriptors, and many of them, and we have also some scaffolds like chemaxon scaffold, silicosite scaffold, CFP, and so on, which could be used for modeling. In addition, if you upload conditions of experiments like pH, ionizable state, whatever, you can also use them as descriptors. So if you are modeling a boiling point, of course, pressure will be very important, and you provide a descriptor for your model development. This is about descriptor representation of chemical compounds, and apart from this, we have a number of models. And I will be showing this in a minute on the OCHEM website, but just to show you that we add all the time new models which appears in literature, which provide good performance, and try also to support them. The issue that, for example, if you're using modern models like deep learning methods, they frequently change due to update of environment and so on and so on. So basically, quite a lot of efforts is done to support these algorithms working all the time. So we update our system, we add new methods, but at the same time, we test that they are working in the same way as they were originally published. And last, validation. We have different methods to validate models, develop models. It's end-fault validation, bagging, and you can select how many faults you would like to use or how many bags for bagging approach can be used. In addition, we have also certified cross-validation, and also recently was added scaffold validation, so you can make validation by scaffolds. So these all tools are available on OCHEM and can be used for any type of model development. So, well, this is our idea of using OCHEM. We believe that OCHEM provides different implementations, different methods, and allow us to capture full picture about QSAR modeling. Thanks to this, we can really comprehend the activity property relations in the most best way. And even if each of tool is not perfect one, because maybe 1D representation not good one, 2D also lose 3D information, and 3D information is too complex because we don't know all conformers. But by basically using all these different methods, we can have best results because like knowledge comes from the different approaches that come together. Okay, let's go again to OCHEM. So I'm just sharing now here. So let's go to OCHEM and let's try to make some model. The model is what we would like to do. And where we can take data, by going to properties, selecting some molecules and modeling them. Or we can do even better because not all properties which were uploaded to OCHEM are really were controlled by quality. It's quite difficult. So we have colleague, she's trying to check quality of uploaded data, but until you model data, you're not sure whether the data correct one. And we don't have possibility to model all data which are uploaded to OCHEM. So some of properties may be mistaken in the sense that, for example, sometimes when you start to model properties, we see that some were measured in one type of units, but by mistake, the data were uploaded to OCHEM with different type of units. And this is happening not only to new data which we collected, but data which comes from already published articles. Sometimes there is like 3 log units, like we analyzed recently one of the properties, and we found that data with different units were reported the same unit, and was 3 and 6 log units difference between some measurements. And people didn't see this. They just make model, and our model was working so, but it was working. And of course, it doesn't make sense completely. But such problems can be still okay due to data which were not perfect in time of uploading. We can't control this. However, we have very good data sets which were already modeled, and you can go to database baskets and here show public sets. Here, all the sets which are publicly available, and there are quite many of them, they were used in some models. So these data are of much better quality, and if you would like to start your modeling efforts, you can possibly go here, select some data sets, and try to work with them. For example, the latest data sets are coming from TOX 25, EOS 25 challenge and TOX 24 challenge, which were run in 2024 and 2025 respectively. And these data were analyzed by many people, and they are on OCHEM, so they are good quality, and if you would like to start them, you can just use them. For example, here we have training set for this TOX 24 challenge, data for EOS challenge. They are much bigger. It's about 100,000 compounds, and we have also 4 properties, so it's much more complicated data, and I will not show them, but for example, for this data, it's quite easy. You can develop models very easily. It's like 1,000 compounds, it's not much. But even we have small data set. We have one of the first data set which we are using. For example, piriformis, it's a toxicity against aqueous species. It's one of I forgot its name of this. It's not bacteria. It's like a little bit bigger organism. But we have this data, and for now I will be using BCF tutorial because it's very small set. It's 179 compounds. I can run calculation as fast as I need, and can show you this in online real time. How you can make this data available for you? You just go to edit basket here shown and create a copy of this. This will create a copy of data, which will be only for you, and use the data analysis. Since there are 2 baskets of interest, I can do this the same for BCF tutorial test. Go here, just create a copy of this basket, and now these were public data sets. Now, if I disable, I will see these 2 sets under my account. So now I have these sets. Nobody can see them. It's only private for myself, and I can do with this data whatever I want. Another way you can do this by selecting data. For example, let's say you can select some records, make some filters. You can select all the records by the filter, and you can, for example, create new baskets by clicking here and create new baskets like a new train set. Problem with double digits, double numbers, double letters published somehow, and molecular sets. If I go to database baskets, I will see this new data set created, and this data set I can use for any type of modeling. So let's try to create first model. We have created data sets by duplication of existing records. By physically, records are not duplicated. Records something which exists in OCHEM, but you create baskets with reference to records. So records are the same as in other sets, but you can now work with this combination of records and to do some modeling. And the models, create a model. I just select training set. So here, when I create a model, I can select training set. I can select validation set, for example, and like test set. And after this, select some method. Select what kind of validation I would like to do. So by default, it's a neural networks method. select, for example, enfold cross validation, keep all other parameters as default. For the first model, no change here. Just click next, and this will go to the next step and will allow us to create model. So it should be going. Yes, here it went. Here's all data which are used for modeling. They always pre-processed, sense that we are trying to use data normalization. We try to convert chemical compounds to same representations and standardization, utilization, and remove salts. And we have CDK, and this work thanks to Martin Sicho. He was doing this part when we were moving OCHEM to the also to GitHub. So he was very influential to add this standardization. Before this, we were using Chemaxon, but now by default we have CDK, and it's work of Martin. So we select here this option, keep them, because usually we would like to have compounds neutralized without salt. We would like to also maybe remove something which related to the 2D representation. And the next step will be descriptors. Okay. Here we have a lot of descriptors which can be used for modeling. Again, if you don't know, I can just use default ones. So we just don't change anything, just click next. We go into the next step. Okay, here filters of descriptors. Idea of the filters to remove collinearity of descriptors. Sometimes we have very similar descriptors which are highly correlated. There is no much sense to use them, so we just delete descriptors which are very correlated, like more than 0.95. This correlation coefficient between them, and also descriptors which are very rare. For example, we have all of the same type. It's no information, or maybe big one. Could be some kind of errors in the data processing, so we would like to get rid of them. I would say this basically almost never filtering. This filter almost never used. So maybe at some moment I would drop it because like basically we don't have errors. If there is error, usually molecule just don't calculate at all. Okay, next step is methods. Again, some parameters. You don't know about methods, so no problem. Next step, and now it comes to start calculations, and you just launch calculations. And calculation will be sent to OCHEM servers, and after a few minutes, they will be hopefully, working. So yes, task started. You can follow this task, but you are not obliged to do this. You can always just go to do something different, because task will be run automatically, and once it will be finished, the result will be shown, and will be shown here models, and here we have view pending task. So models view pending task shows steps of analysis of models or application of models, and you can always just disconnect from your computer and come tomorrow, for example. Sometimes calculation can take even days, so even later, and to see whether results are ready. So that's running, and once it will be ready, we will see the report that was done. So this is basically one way to calculate. It's quite easy, and this was example of descriptor-based method, neural networks, which uses presentation by LogPS. We have used descriptors and OE-state, but there are also methods which do not use any descriptors. These are representation learning method. This method learn descriptor by itself directly from a chemical structure, which can be smiles, which can be chemical graph, and they learn descriptor by themselves. Let's do model of this type, create a model. And here, for example, transforming CNF method or transforming CNN. This method which were developed in my laboratory by Pavel Karpov, transformer CNN, and by myself, transformer CNF, and also with help of other colleagues. And we can select of this method, and you will see that we will be missing one step, descriptor selection. So we have the same method processing, the same step, but after this, there is no descriptor selection because we don't need descriptors. Descriptors will be calculated by the methods themselves. In fact, they are already pre-computed. This is method which learn internal representation during the pre-training step. And there is a step just using descriptors, thresh descriptors missed, and you can just calculate develop model again using default parameters. So again, we started. It's again going to the stage where we need to wait until results are ready. And if you go to pending task, we can see progress, what is going on. You see, by the time when I was trying to start a new model, SNN already finished, and we can see results for this model. To access results, you can just click here, and you can see performance of the model for training and for test set. And it shows different statistical parameters like correlation coefficient, coefficient determination, root mean square, mean absolute error. And you can also visually see how the correlation between structure and properties was found by neural networks. So, okay, you have developed the first model, and what we can do with this model, well, we can save this model, because so far we have calculated model, but we did not save it. So there is a step which is maybe not so clear why it should be done, but basically we say, okay, this is a good model. Let us put it to another database where we will store these models for a longer time, where we can apply these models to new data. So once you click save, this model will disappear from the task of append task, but it will in fact appear here, apply a model, and you will see your model here. Your model moved from, let's say, one tab to another tab, but in fact, physically, it corresponds that we are moved from one database to another database. And once it's done, you can now apply this model to new data. For example, you can select one molecule, you can upload data from a file, you can try to find molecule by class name, and so on. Or you can also apply to a previously prepared data set. So why not? We can apply, for example, first to one molecule, just click start, and the calculation will be running. Now, here are baskets. We have two sets, training set and test set. Let's do something interesting. What will happen if we will apply model trained by OCHEM to set itself? Performance which we see, we in OCHEM report cross-validation results or bagging results. So whatever you see in OCHEM, it's always predictions. We never show results when molecule is used in training and it predicted, because it doesn't make sense, because training algorithms know about this molecule, so there is no sense. We will have much better results. So let's see what will happen if we will apply model to the training set itself. But before this, I can show you that we have different ways to see models. So you can see models, multiple models, by clicking this icon, summary. And what is nice here, by the way, you see another model also finished already. You can see multiple models which were calculated with the same basket simultaneously. So you can analyze them simultaneously. You can compare them to see which method is best one. And okay, for validation set, for example, the performances of both methods even more similar than for training set. And here there was very good performance because BCF bioconcentration factor correlates very well with LogPS, with LogP. That's why this model is much better than model based on representation learning, where method had to learn itself this, but it does not have information about LogP, so it's performing a little bit worse. But anyway, these are always predictions. So these are results calculated by cross-validation. And this is basically, we show to the user situation which is as much as possible similar to real predictions. When you develop model, you don't use any information about training set. Sorry, you don't use any information from test set to select model. So basically, you develop model using training set that is applied to test set, and in this case, you are getting correct prediction of non-seen data. So we simulate this by using cross-validation. We develop not one, we develop 5 models, and each model predicts particle compounds which were not used as part of the training set. And after this, we join these 5 predictions and show the cross-validation. The final model, which stored in OCHEM, is model which is built with all data. Now, let's see, as I said, let's apply this model to the training set. We have here previous state. This is the same set as set for which we develop model. You can just select this set, and let us see how different will be results for the same set which was used and estimated by cross-validation, and set which was just to which we applied model. Okay, once applying, you can see here model. So everything whatever is calculating still, it's pending task. Go to pending task and you see results. Here, this one molecule was predicted. And if we click here, we'll see model itself. If you click here, we see predictions. So now we see predictions. Okay, it says predict values 2 log units plus minus 126. It's quite big standard deviation. Now confidence intervals. And estimated root mean square, we don't know value, but we can estimate based on the so-called applicability domain like this. And we can look, for example, what are the prediction neighbors? Do we have similar compounds in our training set? Okay, there are some compounds which are not exactly the same, but to some extent resemble structure. So this information could be useful, for example, maybe for application in regulatory aspects, because you would like to see whether the training set had some similar molecules, and this will be shown here, whatever was used. Let's see whether model was finished. Yes, it was finished. Again, now you can click here. We can see predictions, and yeah, we have all the same values. And here there is very nice option in OCHEM. If you have a data set, test set with some values, you can add this data set with predictions to the model. So you can make model. After this, you can apply this model to new data and add this test set as part of the model. Let's do it. Add the results as validation set. We click, and this will be shown. Now we look for performance, and you see this is the same data, same model, which was estimated by cross-validation, and this is where model was applied to data which were used in training set. So it's a big change in performance. We have much more root mean square error, and this reflects the fact that basically compounds were memorized by neural networks, and that's why it was very happy to just retrieve its memory from its weights, predict values, and this performance is not really a true one because this performance is only because we predict the same compounds as part of the now test set, even their training set. So this basically important point. QSAR had a lot of critics previously because of problems like this. People frequently reported not real predictions, but they reported just fitting data, and sometimes people do variable selection, a lot of different stuffs, and which also becomes part of modeling efforts, and results which are basically predicted over-optimistic. And these results, for example, can be published, say, okay, well, my model was like this, but once you apply this model to real data, you will have this performance, well, real performance. And people say, no, but it doesn't work. And OCHEM tries to avoid this because, yeah, we always provide not this overfitted results, we always provide real predictions which much better correlate with the performance for the non-seen data. Okay, so this was here. Here can you see the same button, tabular representation. You can click and you can see now from different place we can come to this presentation. Again, we see another method. Let's save this method also. So we have save methods. And also we go to baskets, we can see the same representation here. So basically now we can click and we can see our model results. So you can see it from pending task, you can see it from baskets, you can see it from apply model if you have save model, and you can go to this tabular representation. So by this way, you can develop different models with different descriptors, but it's quite time consuming because each model development requires clicking, selecting data set, clicking methods, clicking descriptors. Is there a better way in OCHEM to do modeling? Models, yes, have so-called create multiple models. We have so-called comprehensive modeling. And this is place where you can develop multiple models with just few clicks. Because basically, as you saw, we use the same protocol, we use the same cross-validation, we use the same preprocessing. So why should not we do it in one click, and why should we do it for each model? If you go to create multiple models, you will have a little bit different interface. First of all, you can select S for one model development, you can select training set, you can select validation set, you can select two validation sets, no problem. If you need, you can select, and I will show you that results will be different. You see, I select the training set, I select the same training set as validation set. Let's see what will be result of model development, because OCHEM is clever about how to handle molecules which are in the training set and the test set. And after this, you can select different methods. Basically, we have different descriptors, and you can develop many models. And for example, if you don't know, you can select, for example, all descriptors. I would like to do them with deep neural networks. I would like to see which descriptors are working the best. And well, we have done this, and you can just create the models. And OCHEM will start to develop multiple models for you with using the same protocols, because we use the same descriptor selection procedure, use the same model validation procedure, and only what is different are methods and different descriptors. Here, it's estimated that 85 models will be developed, and it's only 20 models are started. Why? Some combinations are not compatible. Transformer, which are descriptor repetition methods, and you see this by no descriptors in indication, they are not applicable to descriptors, and they could be only working with no descriptors method, descriptors, so it's basically no descriptors. And combination like this, transformer CNN with Dragon descriptors will be just not started because it's not compatible. Same way, deep neural network method requires descriptors, and here, if there are no descriptors, this method is not applicable. So I can just looking what are combinations which are compatible, which are not compatible, just start those which are compatible ones. And you see, just with a few clicks, I'm starting now 20 models, and it's save me time, save, yeah. I don't need to click all the time, but I will have quite a nice full picture of performance of different methods for different descriptors. So what can be said here? Always start, if you like to analyze different descriptors, just start with one method. Not try with different methods, because there are steps which should be cached. Some descriptors are very difficult to calculate. Some of them can take minutes to calculate, like pi descriptor, for example. It's the descriptors based on 3D structure of chemical compounds. And once you do this with one method and wait until model finishes, all these descriptors will be cached. So they will not be calculated, they will be retrieved from cache. Calculation will be, analysis will be much faster. That's first one. And second, you don't basically need all combinations of all methods with all descriptors, because some of them will be not working with whatever method you use. So there is no need to do this. Okay, model started. We can look here, for example, what is running. And yeah, we will see now different methods, different combinations with descriptors, and possibly some results we are already calculating, and they are retrieved from database, which takes a little bit of time. Let's just wait for 1 to 2 seconds. Okay, so we can see now results. Another browser, and you see methods are very fast, and while I was just starting them, already some models were finished, because like 100 compounds, 200 compounds for chem is nothing. It's very, very fast platform, and there are many servers running on the backend. You can see results very fast for all these approaches. And now we have these results, and we can see that, okay, deep neural networks, for example, provides good prediction performance using LLPS. Nice, let's stay. Nice method. Whatever else, not bad with CDK, also save. Some other method I don't know, because I would like to see other descriptors. Let's wait for a few seconds, we will see performances. Maybe also other method, which are representation learning method, will be shown. So it's kind of, let's say, analysis of 100 molecules very, very fast. Okay, so it's still retrieving results. And OCHEM has two phases. Once it's retrieved models first time, it calculates statistical parameters and saves them. Next time, it will be much faster. So now we see many models finished. And for example, CNF2 was a good model. ChemProp didn't work very well, but Transformers differentiation was working very well for this. So, well, as we say, there is no free lunch theorem. A priori, we don't really know which descriptors will be working well with which method. So one of the ideas will be just to run all of them and select those which are working the best. So that's what I've done. And now, for example, I say, well, it's interesting. Yes, how did SNN would perform for the same descriptors, which were good for deep neural networks? This can be done very easily. If you click on this triangle, and it says create models for those saved in the first column. So it will create models for those which were saved by you, and not for all, because we are not interested to see performance of models for descriptors which do not work very well. We just would like to do something where it's interesting for us. Once we have done this, it will just start few models which were saved by us previously. It should be first column, because it doesn't look for all saved, but first column. And here there was no models here in the first column, so it takes from second column. So it's running. Okay, what about other methods? We have more methods. Let's try to maybe more different methods investigate. We can go again to this interface, select the same data, validation set, test set, training set. You can select, okay, let's look with all these methods which we have. Classification will not be working because regression problem, so you can disable it. And here maybe you can just select, okay, let's say CDK descriptors. And we just click create the models. And now these methods which are not compatible with descriptors will not be started, but all other will be started. We start like 9 different methods, and results will allow us to see how different methods work with these different descriptors. So that's again quite fast. So basically, you are online. If you have access to computer, you can also try to run. You can make a copy of your training set, this tutorial test set, and try to run online and try to see what kind of models you can create. You can see how easily it can be done. Okay, it's starting. And now we go to basket summary, and we will see that we have added several different columns corresponding to new methods, which we just would like to compare with deep neural networks. As by default, we select deep neural networks because this method provides usually the best performance out of all other methods. Not always, but it's one of the best methods. That's why we would like to see it's a method used by users as the first one, because it possibly don't need to do anything else. So now we have many more modules running, and now you can always complete missing rows or columns with just a few clicks. So we'd like to do like this. It will be just one model. You just click. You can just click next, next, start calculation. So we just did one calculation, one model, and we can do it also by whole code. Here we have only one method, not interesting. Let's maybe save another one. So Alva desk were also performing very well. Save this model, and let's say for SNN we say okay, create models for those in the first column. It will create 2 more models. Here, SNN, we have 2 entries because there is some small difference in settings, some settings which were in multi-step, multiple models interface, and those which were when I created models by manually. And if you use template-based, you will have exactly the same settings of the models. Basically, this will not influence results. You will see it will be similar, but it's like OCHEM a little bit distinguish some differences in the settings or parameters of methods. So it's running, and again, something was already finished. It's retrieving results, but we can see whether we have some other methods working well or comparable to the deep neural networks. Still running. We would like to see also this method. Do like this, click, and create models for those. Yes, just create 7 missing models because here there are no saved, and it will just complete a whole row with the missed models. So that's kind of easy. And working with such matrix, you can do really much faster. You don't need really completely fill in all the cells of this table, but you can just very fast go to the most interesting method which you would like to keep for your final model. Done. Okay. Okay, done. We make again update. Maybe also we can do here also, let's say create 9 missing models. Again, we'll add another row with predictions. And once done, yeah, we'll see results and how we can use these multiple models for something useful. While starting, again, you have started, don't need to wait. You can just close it because it will be running in the background. And let's go to basket summary again. That's models are started automatically. When you started, you can quit and you don't need to wait until it will be finished. Okay. It again retrieves a lot of calculated models from the database, index them, and it takes time. Because the most long step is retrieving of all molecules from database, and for each model it's done again, again. So it takes some time from OCHEM to start it. Okay, still waiting. Okay, now you see some models started, some still starting here, and some models finished. And if you just look what is available now, we can see that okay, there was still some small variation. SNN with these parameters was a little bit different result. I was expected would be very similar, but this statistical variation could be due to initial weight, initialization network, and so on. But the results are very similar, and in fact they are within statistical uncertainty. You can hear here, let's say 0.58 plus minus 0.03, and here you have 0.6, so the confidence intervals overlap, and basically it's 0.59, sorry, 0.58 to 0.59, so it's even more close. They are very, very similar. Okay, and once again, refresh, just to see which other methods also provides good performance. If you look here, SNN is the same method, so basically doesn't matter for us. But out of other methods, look like what here it's good. Random forest provides quite good performance. Let's see for other descriptors. And maybe this method, yeah, also good one. It's provide better result in DNN, for example. So this method, maybe it's more appropriate to this data. And if you'd like to check this, okay, so yes, 54, 69. So yes, really this method provides better results, even better than SNN. So now we came to a point that, okay, XGBoost also, but it was a little bit worse. But now, for example, I would like just to see performance of this method for all descriptors, because I would like to have really the best results. And I just create all missing models. So after this fast analysis, I came to conclusion that for this particular property, possibly a random forest method is the best one, and I would like to use this for my final model development. So again, start all of the descriptors, because why I do this, why I'm doing this, because maybe some descriptors which provided high root mean square error for deep neural networks will be better processed by random forest and will have better models. And we, of course, would like to have the best possible models. It's, but I don't, I didn't really fill in full table. I just fill in partially this table. I didn't start many calculations which were not really necessary. Otherwise, we would just overload OCHEM. We will make calculations which basically for nothing. But in this way, I did quite sparse and fast analysis of the data that we have. Okay, 13 models started, perfect. And once they will be finished, we will have full picture of random forest for all the descriptors here. Now I said, let's look how OCHEM will be working with duplicates. So we had training set, we had a copy of training set, which are exactly the same molecules. And now let's look for the performance for these validation sets. So, okay, this was we added, I think, manually. And here we have added by from the very beginning. We added this calculations set was added from the very beginning as a test set for multiple model development. So if we open this model, copy of tutorial test was same. It was new one, but here performance exactly the same. So if molecule was used as a part of training set and the test set, and we provided test set during initial phase, we will see for the test set molecules real prediction. Why it's done like this? Because we would like to estimate some performance of a model for some new data, and by mistake we have molecules which are duplicated between training set and test set. And if we have such molecules, our performance will bias because we don't have any prediction, just have fitting results. But OCHEM looks for molecules which are exactly the same as in training set, and for these molecules retrieves predicted values. That's why we have exactly the same predicted values for the training set and the test set, which was included in the training set, but only one time. Once we apply the model after to the test set, the real predictions, like it's new data, will be considered by OCHEM. It will not try to retrieve data. But it's basically, this feature is nice to avoid some mistakes with validation of models when by mistake you didn't remove duplicates from the test set. So it's, for me, it's, I think, it's a nice feature, and that's why we are doing this like this. Okay, let's look what we have now here for random forest. We have start to have too many models, but still okay. Let's make a refresh. You'll see many more results. And basically we'll see performance using AlphaDesk, because we are still calculating, but also a random forest for all descriptors. Again, some models were calculated. Again, first time retrievals taking some time. Okay. Just let's wait a few seconds. And if you're not happy with some method, we can just delete it. For example, we can delete multiple regression. It was failing for some predictions, had provided very bad results. Multiple regression, for example, or other linear methods, people think they are very reliable method because they are linear one. In fact, it's not true, because they are based on descriptors which are non-linear ones. So they can be much more easily overfitted compared to other methods, I would say. So for me, linear regression is not better at all than a more complex method. Okay, we have finished, and now we can see random forest. As stated, we have too many models. I don't like PLS. I don't like MLR. I can just delete. I delete whole row, whole column. Sorry. I delete, for example, second ISNN results. I don't care about them. And now if I just refresh, first of all, we have less number of columns. We can see better results of models. Otherwise, we have too many. We can try to find which descriptors were working the best, and already see something like this descriptors was working quite nice. Dragon, here it was 0.6. It was not best, but here it was 0.25. I just for tested. Let's look for the validation set for the training set only. Okay, so what do we have some good combinations? Yes, random forest was working very well here. Save was working very well here. Save. Let's save whatever was less than, let's say, 6. So we have many more combinations of random forest with descriptors as compared with deep neural networks, which was not optimal method for this property. And we are just making saving all these good models. Okay, and yeah, it's also working well. And we can now make a refresh. And the intense green colors shows us models which were saved. So why do we do this? What should we do with this? We have so many different descriptors. We have so many. We have random forest, for example, and representation learning methods. Can we make use of this? Do we need all these models? How can we report these models, for example, for publication? And the best what we can do in OCHEM is make consensus. So let's make consensus from all these predictions. Let's make a model which just joins the best models which we got. So for this, we will just take random forest and we take representation learning methods, even if they have a little bit higher error, because this method, well, maybe just let's take only transform CNN, the transform CNN-I and this one. Let's see whether we can get something better. Okay, create another model. And I just start to create a model from interface. So I could go to the interface where I shown before, create a model, but I can just make a model from the summary by clicking button, and here create another model using this configuration. Since I don't want to repeat configuration completely, I just keep this one and select consensus model and continue. Next. And here I select models which I would like to add. Let's say all DNN, not random forest model. 7 models. And transformer. And it was this one. And once we select, we just click, now you see, we add model. And here, after selection, submit select models. Models will be added to the set of consensus. And after this, we just click and wait until OCHEM will create average model with all the data which it has. So we have new model, which is basically summary of all models which we have here. We can make a refresh. And this model, in principle, should be more powerful than each individual model because we got knowledge, we got descriptors, different ones. And once we do this model, possibly will be better. Let's see. I don't know yet. Okay, but we can look, just wait here, just refresh. Okay, and here those cross-validation results, but we can have all validation protocols, and we have now this model shown here. This model has the lowest cross-validation performance because it's based on the cross-validation model, so it reuses the cross-validation protocol. And for the test set, let's see whether we're lucky or not. It has 0.48 performance, and what we had here, 0.57, for example. 38, it's a performance for the test set, which was not never used for model development. And here we have like 52, 47, 47, 51, 47. So, okay, some models had better performance than consensus model, but we don't know a priori which of models which has very similar training set performance but have also validation performance. So fact that we are getting the consensus model, even some individual models may have higher performance and lower error, the consensus model will be working still better because it's like accumulator knowledge. So usually in OCHEM development, we suggest to use consensus. You develop models, you select method which works best, you select descriptor which works best, you try to use a combination of different type of methods, random forest, maybe you can also use deep neural networks together, you can see whether that will help. But eventually, you like accumulate different knowledge from different presentation and it gives you better performance. So why do we do this? Now I stop sharing of this and go to the sharing of slides again. So we have this consensus model approach, and now we go to the analysis why consensus is good. So consensus model, it's like averaging of different opinions, like averaging of different results of voting of different people. And the consensus model really take into account all this knowledge of people in audience. So we can believe that its performance should be better than for the new unseen data than individual pupil. For example, they learn something very well, maybe they can't learn everything. And this is really confirmed by different challenges where OCHEM was participating. So in 2023, we won a challenge for prediction of solubility. It was a Kaggle challenge organized by European Screen Port, and a model which was submitted by my bachelor science student. She's now doing PhD. By the way, got the first place. And the problem was to predict compounds which are non-soluble. And data came from European Screen Port, which bought about 100,000 compounds for their testing, and they found later that some compounds were not soluble. Even they used the best method to predict their solubility a priori. They still found that these compounds were not soluble, and say, can we have better model to distinguish soluble and non-soluble compounds? Training set was 70,000 compounds, 15 leaderboard, 15 private leaderboard, and this is how data set looks like. 93% of compounds were soluble ones because they were selected as soluble ones, and 7% were non-soluble ones. And challenge was, can we predict non-soluble compounds for 15,000 compounds from leaderboard set, and 15,000 compounds from a public leaderboard set could be used just to guide whether we are going in the correct way or not. So the results for 15,000 private compounds were released only after the challenge ends. They were not available at any step for model development. So we used OCHEM, we used the protocols, basically by Andy, and selected different descriptors, make average, with consensus model, and this is basically result. The performance of models was estimated by kappa value, which shows how much better models performs compared to the random. So basically, you can have, if you have imbalanced data set, you can have very high accuracy, but it's just by chance because you have just imbalanced data. And kappa values, higher values show better performance. So what we have done develop models using CutBoost, deep neural networks, transformer, CNN, which is an LP method based on smiles, and graph neural networks. And the idea was just really to select different methods, different descriptors. Best one I did, we did together with him the same selection as I was showing before. We just selected the best method, and basically performances of these methods, as we could estimate by cross-validation, were very similar. That's why we joined them together. And here it was the same. On the training set, we did not see big difference. Performances were quite low. In fact, the data complicated, and that's why we say, okay, let's take all this method, make average, make consensus, see what will be result. So now results, we have this, let's say, test set, which was used to judge model performance. This is public leaderboard set, and here performance is done by consensus, but like of one type of models, cut boost, for example. Okay, 0, 1, 0, 3. This is the most important results, and transformer, gave 0.096. Kappa coefficient, higher value is better. So let's say Rachman networks were working, consensus was working best of other consensuses, but for example, transformer CNN was only one model. So it also provided quite good results. Well, not very high, but they were comparable, let's say. If we start to combine them, like distributed-based method and interpretation methods, we have improvement for the test set and also for the leaderboard set, but it's not so important. We really should look for the test set and all. And for the final, once we combine all of them, we got the winning model, which was combination of 28 individual models. Same strategy as I was showing you before was working very well for this challenge, and we got really winning challenge by making this approach applied to the data. So the conclusion was consensus model improves individual predictions, and that was good result. 2 years ago, we organized another challenge. In this case, I was organizer, so I didn't participate to the challenge. Just like was making data public available on OCHEM and supervising the challenge. Everybody could contribute to this challenge. We had about 100 participants, and the challenge was about endocrine disruptor predictions of compounds, whether they could have endocrine disruptor potential or not against transferrin protein. Because if this compound binds to transferrin, they just affect its transport of endogen ligands, and this is not good. We can have all the diseases and all the bad environment effects. And the article, which was submitted to the Cambridge Stock Journal, where editor had at the time the biggest published data set with activity of compound against this target. So it was very interesting, and we made a challenge based on those data. This is challenge setup. We had 112 training set compounds. There were 200 leaderboard set and 300 blind set, and we had people participate in the challenge from May to end of August, and the results were announced on the 1st September. So the TOX24, we really wanted to see what was progress in method development, and the previous challenge of similar type was TOX21, which was run in 2014. TOX21, it's a naval program. It was called like TOX60 for 21st century, TOX21. And at that time, about 40 teams participated. And for TOX24, we had 70-80 teams participating with much wider geographical distribution. Results, so data were published in OCHEM. They are still there. You can download this data. They are in the baskets, as you saw today in public data sets. And the winners, the first place was Amidov team, and there were another 10 teams which had results non-significantly different to the winning team. So this basically, by chance, could be that next time we do this challenge, this team would be winning, not Amidov, depending on the data distribution. So if you change your training set, just like create by selection from the same set, but like randomly, you may have one of these teams also is a winner of the challenge. So basically, all these teams, they're collective winners because results not distinguishable well. And what was interesting that 3 of models at that time were coming from OCHEM. So people who are users of OCHEM were participating to challenge, and they contributed models based on OCHEM. And 3 of the winners were from this type of models which were developed by OCHEM. And let's look for the individual models. First place was Amidov team, so Dmitry Makarov. He used consensus of 4 models, so he evaluated individual models and submitted his final models, consensus of 4 models, based on different representations. These are 2 representation learning methods. They don't need any descriptors, and these are cut boost decision trees method based with 2 type of descriptors. This is his model, and was published in Cambridge Talks journal, which organized challenge. And if you're interested, you can just read about this model. So what was unique for him? He was using mixtures, and apparently somehow for this property there was sufficient number of mixtures that it could using this representation improved the model performance. And models which were based on repetition learning was transformer CNN. This is a model where you run transformer. It's the same method which used like natural language translation, where you have like English to German, and the transformer learns how to translate sentences from one to another language. We did the same. CNF was developed as a method where we canonize chemical structures. We give non-canonical smiles and we got canonical smile. This was a method which was used, and there were 2 variations depending on how we take a representation of molecules from so-called latent space. Here encoder, here decoder, and here we have some representation which is basically have to be invariant with respect to non-canonical smiles, because it's the code to the same representation for the output as canonical smile. This was one method, and here's more detailed architecture, but I don't think I need to go details. And cut boost was a method based on decision trees, where like random forest, it's just like a different implementation of this method, where models were developed by correlated descriptors by decision trees. So that's 2 methods which were used and which contributed the best model. And the second place was taken by Teresa Cirino. She's a PhD student now in University of Torino, and she did use a different strategy. She was first of all using consensus model, again consensus models, 10 models on OCHEM, but she also tried to increase data set by also considering tautomeric representation of molecules. So she increased data set by uploading to OCHEM also tautomers. This is how it looked like. Here one compound, and you can see it has double bonds different. Here, for example, here double bond, but here it does double bond, so that 2 tautomers, and basically we don't know which one correlates better. Maybe in the solution, this tautomers more dominant, and this representation is more correct for the toxicity. We don't know. And when she did this enlargement of chemical space, her model was improved and contributed the best, second best model of the challenge. And here is also an example of different tautomers for different chemical structure. These are 2 approaches, and which were consensus model. The third approach also was consensus model. I don't show here this approach, but basically 3 approaches which were coming from OCHEM to the top models were basically based on consensus. So it's a good approach. You can have good models. Now this year, just like 22nd, I think we announced results. Was another challenge where the problem was to predict optical properties of compounds, and this set is similar to the set which was used for solubility. And there were 70% of compounds for transmittance, 70,000 compounds for transmittance, a training set and fluorescence. And the goal was to predict compounds which have high transmittance, so more than 70%, and those which have absorbing signal more than 70%. So there were only 5 or 6% of compounds which were absorbing more than 70% for 340 nanometers, and for 450 and more, there were several measurements done at different wavelengths. Only 1.5% were active compounds, so they were absorbing more than 70%. So the set is quite heavily imbalanced. Fluorescence, it was even worse. For the more than 450, fluorescence was measured by exciting one wavelength and observing fluorescence on other wavelengths. Only 0.23% compounds were active ones. So it's absolutely heavily balanced the set. And because of this, we said, okay, let's make predictions. People should provide predictions for these two different wavelengths for transmittance for fluorescence. And we take average area under the curve as a measure to predict average performance to find the winner. I said 100,000 compounds were available, 70,000 compounds was available to the model development, and later on we released a leaderboard set of which additional about 15,000 compounds to improve models. Now I show results. I also participated, but as a non-active one, just like organizer. So I did also model myself. So I was able to come to the in both categories, like 10 best models. But the second better models than mine was developed by Marko Jukic, who took 6th place out of the 10 for category of transmittance. So it's, this time, let us say, we don't have so many models by OCHEM contributing to the best models of the challenge, but still, we have at least one is true, and two by me it's like okay, organizers they're not counted, but still show that this consensus approach by basically using the same what I was showing to you. I develop models, make consensus, and provided them for predictions. Did contribute very nice results. So even if it neither Bono neither myself won the challenge, I was not going to win. If I would win, I would take prize. But it was just interesting to follow the same methodology, which was working very well during previous challenges to get this result. So I think we have very nice platform. It's of course can't win all the time. It's would be magic, but it does provide very good results in general. So, and this basically I used the same approach which was used for this two recent challenges. Nothing was changed, and it was working quite well. And I would say that this time, not many people could participate because development of models using 70,000 compounds is quite expensive for him. So Bono asked me explicitly whether I would allow him to use OCHEM for such calculations. I gave him such resources he was able to use. And if other people would ask them, I could give them also resources, but basically not everybody was able to use OCHEM because while calculating of my models, for example, was taking 2 days just to make consensus. I had to really spend 2 days of calculation using GPU, a lot of CPU power. So these are heavy models. They are heavy models, and for such type, you need to have very strong infrastructure. While few thousand compounds analysis for OCHEM is not a problem, 100,000 compounds is already a little bit too heavy. So that's conclusion of this analysis. OCHEM is really offers top tools for model development, and you can look in the articles which we have published about Kaggle solubility challenge, or articles which were published by other people for the TOX 24 challenge, and see how they develop models. And basically, with this approach, you can develop quite powerful models for your use. And this is just would like to finish my presentation. And we have really good powerful tools, and these are things people who are contributing to this presentations of the slides, but I will still go to OCHEM and show something which may be useful. But it's like about slides I will not show anymore. That's basically also support was a chemist project where we have students developing some nice tools for explainable AI methods. That was about this one. I maybe just can, if there are some questions, I can ask questions. If not, I can just continue with, okay. Are there any questions, Pavel?
Are there some questions? Yeah. Do you hear, Igor?
So.
So, okay, I can come.
So a couple of questions. First one, you've talked about consensus models in OCHEM. Can they be automated? Or do you have to select the models that you want to combine them? And if not, do you plan to implement it?
In principle, it can be automated, but it's already quite heavy resources, even for calculating of these models after this. So I don't really see a need for this, because basically once I calculate individual models, for example, I analyze which compound are failing for each method. And then I may correct them, because sometimes you see the compounds failed and you try to analyze and you see, okay, this was solved, maybe it was not correctly handled by OCHEM. So I just try to make structure that will be just like not failing. Or for example, sometimes some descriptors methods, they fail from particular representation of some groups. For example, nitroso groups, sometimes you can present as one single bond, or you can present as double bond, and some method fails. So, well, I'm already user for OCHEM, so I know that how to try to change the presentation that method will not fail. And after this, once I'm removing all molecules which fail, I make data more homogeneous. Data become more homogeneous because nothing fails, and it does improve model. So this philosophy, I just calculate different descriptors. I look for each individual descriptors, whether something fails. If yes, I correct, and by this I improve data. So I would not blindly completely do it, because I would like to see performance each model. And also once we do consensus, it's also sometimes not clear how many models should be collected for the consensus. Usually, like, look what are the best models, look for the threshold, and try to see what models have similar performance. But after this, I consider like things, okay, we have like different representations, different descriptors, but we have also method like deep neural networks. It's neural network method. It's based on the weights, and we have cat boost, which is based on regression. Even maybe one method a little bit better, a second method a little bit worse. I just would like to take all these individual models from both these methods to make the final model better. So I would say that it's not completely automatic. It's not like a complete like tool, like click button, you get results. There is still some kind of things which I look for data and so on. So that's why I was not trying to do it. And I said it's quite difficult. But in theory, yes, you can do completely automatic everything. Just click button, you can run, and after this, you can look, for example, the best model. For the best model, you have standard mean error of your parameter. For example, AUG, area under the curve, or root mean square errors. You can select other methods which are not significantly different. You join them, and you have the final model. Possible, but not done yet.
Yeah, thank you. That's the smart way, I guess. And the other question was regarding, well, the challenges. So in particular, I had the curiosity in the optical prediction challenge, if the first models or the best models, why they were different than the other ones, or what was the difference? And in general, with these challenges, what do you see? Is it model architecture that's driving the best performances, or is it the data selection that you select from the data that you're given? What would you say on that?
Truly speaking, I don't remember exactly description of two models, because these are two teams, two different teams, won two different challenges. This is what is interesting. Both teams are from Japan. That was like unexpected, and I will need to analyze. I think it's method, but also experience, because like the first team, it's they are professor from computer science department in Japan, and second team, I know them for a long time, because they were participating in the very first challenge which I organized in 2009 maybe, or 2011. So this team was already there. They were also winners, but not like the final winner, but all these non-significant different models. So these teams, Professor Uesawa, they are really participating to many challenges, and they were always, I need to say, silver winners of the challenge. So I think it's also expertise. They develop some methods, and they basically have some knowledge in chemistry. And for example, here they try to renormalize data, because in addition to just 0, 1 for transmittance, we provided raw data. We provided raw data. Say, okay, you can use this data for example, model development if you want, and basically they used renormalize the data based on plate. Plate information was forbidden to be used, but it was possible to use plate information to renormalize data for training, and I think it was kind of part of the winning technology which helped them to win. So I mean, I do have descriptions, and winners will be announced in the Boston in 2 weeks, less than 2 weeks from now, and we are still analyzing whether they did not use plate formation, but yeah, it was not used, because we explicitly asked them, did you use formation? Yes, but only for data normalization for training set, nothing for the test set where we ignored any of this formation. So I think it's kind of experience plus methods, which yeah, very good, combines this.
Okay, thanks, and thanks for the presentation.
Welcome. Thank you for the questions.
Other question? There is no other question, so if you have something to show, you can switch back to the presentation.
I think yes. Basically, I'm just showing this OCHEM. I can, yes, I see, you can see it. So basically, this is yeah, these are 2 challenges, and TOX 24 challenge here, and here this Amidov team which won the first place, and Talita Chirino was second place, and this team from Armenia, Professor Yasava was first place, so he was here also. And yes, there was also quite of 11 teams were having models not really different. It's also not yet related for optical properties prediction challenge. I still need to run script. Unfortunately, I was busy. I believe that about 10 teams will be maybe also winners, because scores looks very, very similar. But yeah, so what I'm just trying to say that, okay, you see, same professor here, same professor there. For example, Vladimir Chupakin is here. He also here. Here. Maybe I think no, as he's now significantly different or not. For another model, he's in higher. So basically, I think it's expertise of teams, expertise of chemistry, but also expertise of machine learning, which really contributes to the winners of the model. So basically, like for the previous challenge, TOX 24, innovative part was these mixtures, and innovative part was enumeration of molecules with tautomers. And once we will know complete description of the method, I think we may see some other features which were used by challenge winners, like data renormalization. So they use classification, they change it classes based on the data normalization. They change threshold somehow, because I don't know completely method. They send me code, I can just reproduce everything, but did not really try to completely understand how it was done. But idea was to bring some kind of physical sense to this, because if there is a different, for example, you have transmittance and you have variation between different plates, the threshold which we just fix 70% is not correct one. Maybe in one place should be 60%, another place should be 75%, and we just do 70%, but it's not correct one. If you renormalize data and we use different threshold, we have some compounds which in border will be better classified. So I think it was interesting part of this challenge to come something which is yeah, interesting. And I reported this result to the challenge owner who gave data, and they will say, oh, it's interesting, we should look at this also. So I think we are all learning. It's like we organize challenge and we see the results. I was participating with OCHEM to admit TOX challenge. Unfortunately, I didn't get the good place. First of all, I didn't have so much time. I didn't really have at that time a BC student who could spend for this 3 months. It's, you need somebody, but really I was working on the challenge less than 2 weeks and had other problems. And there, okay, for example, was not really winning. It was like more than middle of scores of people who submitted the model, but it was still good model. So it was still good models, and challenge was there very difficult. You had to predict compounds, properties of compounds, which were at the end of the series development. You have compounds in the beginning, you can measure them, but eventual goal when you make this project, you synthesize or computer synthesize virtually compounds, and you would like to select the best ones on the knowledge which you have in the beginning of the challenge, or this series development. So it's like very difficult problem to basically predict compounds without of predictive domain. So, but still, OCHEM was quite providing good results. So I think it's general good platform, but from this challenge, for example, I see that new methods like new graph neural networks were contributed a lot of good models. There was also tabular representations, tabular transformers were contributed with good models. They are not yet in OCHEM. Oh, will be added because these are good methods. So why should we lose them? So for next challenge, we will have them also. Yeah, that's basically, yeah, it's, I would say that it's very nice to participate in challenges because you are feeling this competition spirit. You would like to win. You would like to do something interesting. Your brain is working differently when you just write article, and when you're trying to compete with on a challenge, you have much more adrenaline because you submit your performance while now at the end. Okay, something went wrong, so I should think better. And this is what stimulates us to work. It's like competition. Sometimes people say, we make challenge, we don't care about who will win. Come on, guys, we are living for challenge. We would like to really be first one. Everybody would like to be the first one. At this life principle, we would like to be the best one. So challenge is a very good, shows that you value something. I'm sorry. If your methods never win any challenge, how can you say these methods are good ones? Or whatever you're developing, why it's of value? No value. Because you always, when you make your model yourself, you can always trick data, you can make some outlier filtering, some other tricks, and yes, on the test set, you are the best one. No, I don't believe this. Go to this challenge, another challenge, and show that your method is the best one. In this case, I trust you. Otherwise, if you are just yourself and claim you're the best, it's no value. So for me, challenge is really something very important. And even if I'm losing, I just say, yes, we did not think about this tabular representation, for example, tabular transformers would be very nice to add them. Why not? Next time it will be better. Yeah, okay, I think that's what I want to say about this, and really, really just promote, if you see some challenges and you have time, of course, because you need to invest, you need to understand this. It's very interesting to participate, and you will get a lot from that.
Yeah, thank you, Igor. Thank you.
Thank you, Pavel, for invitation. Yeah, and I hope next time I will be there in person.
Me as well. Me as well.
Okay.
I just want to remind participants, because your last remarks were very relevant. Tomorrow we will have a challenge, and if you will participate in it, I think that those platforms can be very suitable for participation.
So yeah, if you're interested, you can use OCHEM, of course, for this challenge and see what kind of result you will get. You are very welcome.
It may be relevant, yeah. Thank you, Igor, once more.
Thank you. Okay, bye-bye.
Okay, so we have a coffee break and then the last tutorial session.
Maybe now? Yeah. Oh, okay. So it is at least the room can hear me, but I don't know if people online can hear me. Okay, so yeah, it was a user issue then. Yeah, yeah, there are too many buttons on this microphone. So maybe. Okay, cool. So awesome. But yeah, so basically this is the, like, we are going to aim to generate something that looks a bit like this. So this is just to show you like what kind of structures to look for in the generated compounds, basically. So yeah, you can go through that, and hopefully it's installed for me already. Yeah, it did. It did. So yeah, I'm just gonna check the directories. Yeah, I'm still here. Yeah, okay, so here. I need to change to here. And we check if we can still load the model. Yeah. Okay, cool. Yeah. So yeah, basically you should be here. So yeah, the model should load for you. And what you can do here is try to generate compounds using this model. So a little bit about this model. So this basically comes with DrugEx, and it's a pre-trained model. It's a recurrent neural network, like I was showing in the presentation. And it's just pre-trained on the Papyrus dataset, which is basically Campbell plus some other data sets. And like I said, this general model, it's tailored towards reproducing that chemical space with some random noise. So it's not on its own, it's not actually very useful. So when you look at the generated structures, yeah, here you don't see anything. But what we can do is basically generate some depiction like we saw in the chemical space visualization tutorial. So we just convert the generated ligands to, yeah, I think we changed the batteries. So yeah, so you just put it in the data frame, and then we can use the visualization that you already know from the chemical space workshop, basically using Morgan fingerprints and UMAP with some settings that I found worked pretty well. So you can run this as well. We will see if it will actually show on this computer, because I had a problem before. So yeah, does it show for you? Yeah. Yeah. So here we're using binary fingerprint, and Jacquard is basically the same metric as Tanimoto coefficient. So it's closer to like our intuition of molecular similarity. So this might take a while in this environment. So nice. Did it? Yeah. So now we can plot it here. And I really hope that this time it actually works. Yeah, so did you? Yeah. So yeah, here we're not going to be using the pocket. We will just be using known ligands, and we will try to basically generate some QSAR model based on the activity data, and we will use that as an objective function. But yeah, there are tools to also find pockets on the surface of proteins. So yeah, like I kind of forgot the names, but there are several. Oh, okay. thank God. Here it works. So maybe you have this in front of you then. So yeah, like, I don't know how much time we still have. Oh, we still have 1 hour, so I think it's fine. So there is still time. Like if you are having any problems and you don't see this, I can still check in a little bit. Yeah. So what we see here actually, yeah, this is a bit annoying, but I don't want to zoom out so that you can read the code. So what we see here is actually in blue, we have the generated set from the pre-trained model, and this orange set is the set from Papyrus database. So this is all known ligands, both active and inactive, basically all ligands that were ever tested on the serotonin receptor. And you can see that they basically occupy some clusters in the space, which makes sense because those are the different chemical series in a way that people have tried to explore. And when you look at the generated structures, they are like sort of in the middle. They don't really belong anywhere. So they're not specific to this target. They're just some random sampling from Papyrus. So not really useful if you're working towards some target, but that's exactly what we're going to do in the next part, where we will try to fine-tune this model first to the space that we actually want to exist in, and then we will use reinforcement learning with QSAR modeling to optimize towards more active molecules. So yeah, maybe I will take a short break here just for some more debugging. Maybe, but no more than like 5 minutes, because then the runtime is going to die. So we need to do it in one run. So if you want to go grab a coffee or maybe go to the toilet, then I would say 5 minutes break. But if not, you can stay here. Yeah, so you can run the other code below as well and read the tutorial. So is there anyone who still needs help, who didn't get this chemical space map? Yeah. So do you actually need a break? I don't see people rushing to the toilet, so maybe let's just continue then. Yeah, well, I mean, you can take a break. Yeah. Okay, so let's do like 5 minutes. You can play around in the notebook, but yeah. Yeah, what you can do is also try to run some smart search against these molecules. Yeah, so for example, here I put the serotonin scaffold, I think. Yeah, so you can see it highlighted. So yeah, if you know any serotonin receptor ligands, you can try to put the smarts here and see if they're in the data set. Yeah, I'm gonna explain this after the break. So yeah. So who wants debugging help, or everything is fine? Nice. Yeah, just try to run a cell here and then, so that Google doesn't kill your session. Yeah. We like, there's always problems with this, because last year we were in a lecture room where there was different environments on every machine, so like every person had different problems. So now we switched to Google Colab, but yeah, still like it's problematic as well. switch this back on. Yeah. So yeah, I think we have still 2 people missing, so maybe 1 more minute. But I don't know what's with the microphone. It seems connected here. Refreshed. So let's go on. So I was saying before, this is a pre-trained model that was basically trained from scratch to reproduce the smiles that you can find in this Papyrus database. So what you can do, one method where you can sort of specialize this model quite quickly and using even like small data, because the problem is that the model needs to learn the smiles syntax as well. So you need a lot of data points to basically teach the model how a smile string looks like. But when you already have this pre-trained model, you can use something that's called transfer learning, where you basically take the pre-trained model and then you focus it by giving it like a small set of smiles to adjust the distribution so that it generates molecules that are more similar to the molecules that you give. So this is what we will be doing now. So you basically take like a second data set that can be much smaller than the first data set, and you do the same training as you would do for the first one, and that basically specializes it to generating compounds that look like serotonin basically, and serotonin receptor inhibitors. So this is what we will do here. So with DrugEx, what you have to do first is some standardization. What we are going to do is basically take this data frame where we have these both active and inactive ligands, basically all the chemistry related to this serotonin receptor, and we're going to prepare it. So this should not take too long. So you can run this cell. Yeah, should give some meaningful smiles, and then we prepared the data set. So that's basically what this is doing. We need to encode this so that the model understands it. So this basically tokenizes all the smiles from our data set and creates this smiles data set that we can then give DrugEx, and it just knows how to work with it. So I'm not going to explain this in detail, but it's basically just preparing the raw smiles into something the model understands. So yeah, that should also be fast. And this is again just some more preparation. And here we're actually going to do the fine tuning. So you can try to run it. And normally if you're doing pre-training, it takes a lot of time, a lot of data. But when you're just fine tuning the model, you really need like 10 epochs on your data set, depending on the size, to get a result that's sufficient. So you can just fine tune it on really like tiny GPU these days. So this should only take like a minute. So are we fine tuning? Yeah. Yeah. I'll take a walk again. Tu nie te? Ja, super. Fine tuning. Jesteś na przykład. Some people are ahead. That's good sign. Yeah, fine tuning. Nice. So, how about you? Yeah, everything is running. How about here? Nice, that's beautiful. So yeah, once you get it running and your session does not get killed by Google, then you're good to go. Nice. So yeah, I can see we are fine-tuned. So then we can basically do the same thing as we did before. DrugEx also gives you some useful output files that you can take a look at, basically like the loss and how it developed over epochs. So you can depict it like this, and that basically tells you how well the model trained, basically how well it adjusted to the new distribution, to the new structures. And you can see that already, like after 2, maybe like 4 epochs, you sort of start reaching equilibrium where, you know, the model doesn't learn anything new. So you have really quick convergence, and that's thanks to using this pre-trained model. So I'm just going to do some more stuff. I will generate now new structures from this fine-tuned model and add it to our all-encompassing data frame, where we have the target-specific data, the pre-trained molecules, and now also the molecules from the fine-tuned model. So we can again plot it. And so what should we see now when we plot this? How is this plot going to look like? So some people already have it, so what do you see? Yeah, one more color, and how is it distributed? Yeah, so it's sorry? Yeah, so it should be closer to the data set, to the serotonin receptor data set. So let's check if that's correct. Yeah. So the new color is the green color. That's what comes from our fine-tuned model. I can check the legend here that we are not lying. So you can see that the general model, it really just generates something random in the middle. But you can see that even after 10 epochs, the fine-tuned model basically generates molecules that are similar to the studied dataset. So that's nice. But if we want to generate something that's truly novel, it's clear that this is not it. I mean, you can see some interpolation here. So maybe these points are interesting, but if you want like more enrichment in like novel chemistry, you will need to do something else. So I talked about reinforcement learning. So that's what you can do. So we will do it now. We will just save this again. And we're going to prepare for the reinforcement learning part now. So there should be a QSAR model saved somewhere in the data folder. So we will try to load it. Hopefully it works. Yeah. So yeah, it's going to complain about some version, but if everything loaded correctly, it should be fine. So QSPR-PRED, that's basically our QSAR modeling framework that is quite easy to use. Basically, you can build QSAR models using just like 2 lines or something like that. And there's also, if you go back to the repo and you go to Genovo and you check the notebooks, there's also a QSAR notebook. So this QSAR model, that's how it was built. So it's there's more outputs generated. It's not like documented word for word, but this is basically how you build this model. So if you want, you can later check this code. But I'm just going to continue here. So this QSPR model, it's going to be basically will act as a QSAR model for our objective function. So you remember the project with the synthetic accessibility score and the QSAR model score. So that's what we will basically reproduce. It was using the same code. So what we can now do, we can basically predict, using this model, we can predict smiles. So that's what we're going to do. We will generate basically predicted Ki values, or rather PKI values for our sets. So this might take a while, but hopefully there shouldn't be any problems. Yeah, so so after it finishes, you can also run this code below, which will give you basically the distribution of the predicted activities for this initial set of compounds, because not all of these compounds have measured Ki values. So this is kind of an overview of like you would expect the distribution in the data set to be, but it doesn't mean it doesn't mean that it's like correct. So yeah, this is taking a bit more time, but yeah. Did anyone got through this already? Through this? Yeah. So just takes some patience. 2 minutes? Okay, yeah. Yeah, I don't know why Colab is so slow. Like on the like if you run this natively in a Jupyter notebook, it takes like 2 seconds. Sometimes on Google Colab, like when there is file operations, especially, I think it has problems. Maybe it's the Google Drive thingy. Yeah, okay, it just finished for me. So hopefully it did finish for you, or will finish soon. So you can regenerate this histogram. And this is just basically like our initial Ki value distribution. So what we want to do with the model is we want to generate molecules that have basically the average Ki values moved to the right towards higher pKi. So we will be basically comparing this distribution with the generated distribution to see how we did. And we can also look at the fine-tuned set. So for the fine-tuned set, you can actually see the predictive value is lower, which is expected, because these are just random molecules, and they're also like a bit outside the applicability domain of the model. So and it's very like less likely that if you generate a random molecule, it's going to be active. So you can see the distribution is actually shifted to the left, and this is sort of like what we will be starting from. So we want to shift this distribution to the right, so that in the end we have enrichment in high activity ligands. But you can see there are already like some ligands that the model thinks are active. Yeah, here is just like some statistics, blah blah blah. I'm gonna skip that. You can run it if you want. So yeah, to prepare the environment for the reinforcement learning, so we have this QSAR model, like I already showed. So that's one objective, and then you have some synthetic accessibility scoring. So here we're using Petr Ertl's essay score. Actually, he was talking here on Monday, I think. So you know his face. So we will be using his tool here, and it has an implementation in RDKit. So it's basically you can get it from RDKit. So that's it. I can hear more. Okay, that's not. Yeah, that's not our stuff. Yeah. So this will be. This will be our two objective functions. And yeah, what you can do here with these scores, like you can calculate the scores for the generated molecules if you want. So you can check the distribution. Assay score, basically, it goes from 0 to infinity. And the higher the value of the assay score, the less synthesizable the compound is. Usually, like the maximum is around like 4.5 for the assay score. So if it's higher than 4.5, you usually don't want that kind of molecule. Then it's too complex, especially like for an initial hit. So you can see that a lot of these molecules, they're actually quite complex, have really high assay scores. Like sometimes the threshold people say like is around 6. That's like natural product like. So this is quite arbitrary. And yeah, so here I'm just doing more scores, whatever. So one important thing that you want to do before you do the optimization, because you have basically two objectives that are on different scales. So the pKi prediction, that's basically from you saw the distribution, so it's like around 7 average, and then it can go like a few log units down, a few log units up. And the assay score can go to infinity. So you need to scale these values. to the range of 0 to 1, ideally, or some constant range, so that you can use it for optimization. Because if they were on different scales, then it would cause problems when you're giving the reward. Because the higher the value, then the more reward you would do. So it would not account for the objectives fairly. So that's why we want to have these what we call score modifiers. So there's a range of them implemented in DrugEx. For example, here I'm using this clipped score modifier on the QSAR model. This is what it looks like. I will explain it in a little bit. So this modifier basically it transforms the predicted PKI value, which you can see on the x-axis, to let's say desirable values. Because let's say that we consider all molecules that have the predicted PKI lower than 7.5 inactive. So then we want to score them basically as 0. These are undesirable molecules. So that's what the clip score is telling here. And then as we approach some maybe like satisfactory value of the predicted PKI, then you want to increase the reward for the model. And then when the molecules are, let's say, like 8.5 and more in predicted PKI, then you're satisfied. So you just give one, I like this. So yeah, so this is basically how you set up the objective so that it reflects the desirability of the generated molecules. And then for the assay score, we do the same. So again, we use this time smooth clip score modifier, which is similar, but looks like this. So like I mentioned, assay score, it can go from 0 to infinity, and around 4.5 is kind of like the ideal cutoff for like a hit molecule that's not so complex, but we can still optimize it. So we consider everything that's higher than 4.5 as basically undesirable, and everything that's lower than that, we say, okay, we like this more and more and more, and if it's around 3, then yeah, that's great. So yeah, that's basically this modifier, quite easy. Yeah, so here's some more histograms. I think I'm not going to go into detail here. This is just like the histograms of the assay scores, PKI values for like the initial set. So I'm not going to do it. So here, all we need to do, we have our scores ready. We have the modifiers in place. So we basically just create the environment for the model. So that's just the scoring functions. And we define some thresholds to use as like desirability cutoffs. So for example, for the assay score, we have the 0.1 as the cutoff. So that's already referencing the modified value. So that's basically here. So when we look at the statistics, like basically desirable molecules, like they start at around 4. So like 4.5 already like is too high for us to consider them. So that just affects the outputs of the model, not much more. So yeah, so that's 0.9 and then 0.5 for the QSAR model. So yeah, if you run this, hopefully it creates the environment. Then of course you can use it to like generate both scores, get a data frame if you want to do some post-processing, whatever. But here you can see the modified scores and if it's desired or not. So the molecule is desired when it has values for both of these objectives above these two thresholds. So that's easy. You can also get unmodified score, so of course, from this. So this will just give us the raw values. But what the algorithm uses are these two values, those modified ones. Okay, so then this is going to be hyperparameter optimization among us, like parallelized across participants. So yeah, so who's actually following and calculating? Hands up. Yeah, cool. Okay, I count that as a success. So we will split into 4 groups now. So maybe let's do it like randomly. So you just pick one of the groups randomly, and you try to change the code here below, like it is written in here. So for example, let's say I'm group 3. So I want to set the epsilon parameter higher than 0.4. So how is higher than 0.4? So let's say 0.8. So I will explain the parameter. I already explained it a bit in the presentation, but I will explain it while it's calculating because this will take some time. So I will set this to higher than 0.4. So if you also want to be group 3, choose a different value than 0.8. But it needs to be higher than 0.4. Yeah, so like you can, if you're working together, you can sort of like, there's 3 people here, so you can agree like maybe each of you can be in different group, or if you're in the same group, just choose different values, but still respect like these rules. But it also says here that I should switch the agent and mutate network. So I'm going to explain it. So I'm just going to do it quickly so that I don't forget. So switch agent and mutate. Yeah. So that means that I will switch the mutate network for a pre-trained model, and the agent will be the fine-tuned network. So I will do it like this here. Yeah. So if you're 1 or 2, you don't do anything with these parameters. If you're 3 or 4, you switch them around, like I just did. So the fine-tuned model in this case is the agent. So that's, during the presentation, I explained that the agent is actually the one navigating the environment and the one that's being taught basically how desirable molecules look like or not. And the mutate network, or the exploration network, as we call it sometimes, is the pre-trained model. So that one is fixed, and it basically adds some random general inputs to the agent. And the epsilon parameter, it basically affects how much this mutate network mutates the output. So in this case, we're basically starting from the fine-tuned space. So that's like serotonin-like space. And then we will use this general model to introduce some noise, and quite a high amount of noise, because we set our epsilon to 0.8. So this way we can basically start from our fine-tuned data set, but then explore a little bit more by giving it some random noise. Yeah, and the different values of different parameters that you chose, they mean different things. So if we started from the pre-trained model as the agent, then we start from general space. And if we set higher epsilon value, then the fine-tunement network will have more influence. So it will try to narrow down this space. And this is all like regardless of the objectives. And then you have also the objectives in addition to optimize. So it's like a multi-pronged optimization. And those are basically the hyperparameters you want to tune in DrugEx. And it's basically the trade-off between exploitation, exploration kind of thing. So yeah, so let's run it. It could have been running while I was talking. So yeah, just run your code. Let's give it 50 epochs. And we will see how long it actually takes, because how much time do we still have? Yeah, so we have half an hour. It should finish in half an hour. We will look at the estimate. Yeah, so that's 30 seconds per iteration. Okay. Yeah.
Sometimes when you use a model to try it can repeat the get out
Yeah, so yeah, in this case, we don't account for that, so we will probably see it in the outputs. But yeah, what helps is you can add another additional objective function that basically tries to mitigate some artifacts that you see in the output. So it's usually kind of an iterative procedure. Like I said, reinforcement learning, it's stochastic. So even if you run it 2 times, you get different result. So you usually like run it a few times using different settings. You look at the outputs, and if you see some artifacts, then you try to think of an objective to add to mitigate it. But since with this model you can easily generate like 1 million molecules, even more. So if the artifact is not there that often, you can just filter out maybe like 200,000 molecules, but you're still left with like 750, like 250,000 that should be okay. So depends like if you want to mess with it or not. Yeah, so yeah, this is slowly continuing. So I think maybe you're continuing at the same pace. Yeah, so now we can have a longer break. Now the environment is working, so I don't think it will crash on us. But basically, when this finishes, yeah, you can see that sometimes it tells you that it's calculating the policy gradient. So that's basically the mix of the distributions from the 2 networks plus rewards for our objectives taken into account in the agent, because the agent network is the only one that's being adjusted. So after we're done with this, we will take a look at the molecules, and you should get different graphs like this, so you can compare among each other, and we will try to find the best set of parameters to give us basically the highest desired ratio. So you can see in this case, it was actually not that high. Somebody will have better success. So we will see where we end up. So this is, yeah. Yeah, so this is gonna take some time. So if you want, you can, yeah, or you can lower the number of epochs. But so we have like consistent like level playing field. It would be nice if you can keep the 50. Yeah, so it's gonna take maybe like 20 minutes. So yeah. So this like, if you still need me to debug anything for you so that you get to this point, now we have time. So yeah. let's do the final analysis and then we can get out of here. So yeah, for me it finished. So just to repeat, we switched the agent and the mutate and the exploration network, and we had epsilon of 0.8, which means we have higher influence of the like generic pre-trained model. So yeah, here we can see some summary of the training. So yeah, 50 epochs. And we take a look at this graph. Oh, what the? Oh, okay, I didn't. Of course, yeah. Did not create this data frame. So okay. So probably you have better figures. So who had the highest desirability? So who had more than me? Yeah. So how much? 0.4? 0.4? How much? The blue one is the desired ratio. 0.1 as well. Yeah, so 0.4, yes, I was hoping for higher values, but yeah. So nobody has more than 0.4. So what was your setting then? What? Okay, yeah. So yeah, like that's yeah, I think the optimal parameters when I played with it is do not switch it and like 0.2 for the epsilon. That's what you did, and you also got like 0.4. Yeah, yeah. So yeah, this is like in terms of desirability, like really bad result, but it's kind of obvious when you think about it, because here I really hiked up the influence of this pre-trained network. So it's really generating in this generic space where it's really hard to find active molecules. And active and basically reinforcement learning alone is not enough to find anything in this space. And we're also not optimizing the agent. So because if you have too high of an influence of this exploration network, then it's just going to reproduce this distribution and not actually take into account the reinforcement learning that much. So also like you want to set this epsilon value reasonably low as well to basically balance out like these two objectives, let's say. So yeah, so this was not really great. But what the analysis that you can do here is basically like you take the agent, which is like the supposedly trained network. So what the DrugEx does, it will save the best model. So the model that had the best desirability, which actually probably is the first model here. but for you, it was maybe like, I don't know, 30th epoch. I don't know. What epoch was like the peak for the two people who had something reasonable? 48. Yeah, so like here, yeah, that makes sense. Yeah, sometimes like we didn't train for a long time. Sometimes what you see like that it really doesn't catch on in the first 50 epochs, but then it starts picking up. And it's also what maybe affected my result here is the number of generated molecules per epoch, because the more generic the model or like the more difficult the objectives, then it's strength in numbers. So if you increase the generated set at each epoch, there's a higher chance that you will actually find some decent or like sort of good solution that the model can then pick up on and create a pattern out of it. But if you generate too few molecules, like 1000 is not enough, then it doesn't have enough information to at least find like something to catch on. So yeah, that's what we saw here. Yeah, so we can generate molecules with this model. It's basically going to be really generic space, I think. Yeah, so yeah, we generate 1,000 molecules. So you can also generate with your models. We've probably done that. You can generate your molecules, and then you take a look at the depiction. So for what so for the best models, like what does the depiction look like? Where do the molecules that you generated fall into? Are they like different from the fine-tuned set or similar? Mm-hmm. Yeah. So that's exactly like kind of the trade-off that we are aiming here for, where you want to have some interpolation basically between the generic space and getting closer to the areas of serotonin-like ligands. And then maybe some sweet spot is somewhere in the middle where there's maybe like a new chemical series that you can find. So yeah, let's just turn this into a plot, and then that's the last part of the workshop basically. So yeah, you already have it, but for me it will probably look a lot like the pre-trained set. So probably should have chosen like more sensible parameters to show, but in the spirit of the challenge, just went with random. Yeah, okay. Yeah. So I think that's the purple color. Yeah, so that's the reinforced one, and you can see that it's like really in the middle, but actually, like there might be something, some like a few molecules. Like you can see it also like starts to spread out a little bit. But yeah, like basically what you're looking for is maybe like hints of this, like where you start getting clusters in like unexplored areas of chemical space, like where you can have something new. We don't know if it's active here. So I think we have predictions for each generated molecule here. So this one is like, somewhat predictive active, but yeah, I wouldn't have high hopes for any of these because the hyperparameters were not great. But what you can also do, I hope I'm doing it here. Yeah, I'm doing it here. What is useful to look at is basically the overlay of predicted activities across the sets of interest. So here I'm actually taking the pre-trained set, the original biological data, fine-tuned set, and reinforcement learning, and I'm coloring everything with by the predicted pKi value. I think that's what's gonna be here, or it's just gonna show on the I'm coloring it by the predicted pKi. So some of those don't have it assigned, so that's the black ones. But this is a useful plot to basically pick out some like highly active molecules. So like the closer you are to yellow, then the better. So you can pick out maybe like this one, like that's the like 7.6 and like somewhat novel. And you can see that it makes sense. Like it's quite similar to the molecules in the original set. So this could be like an interesting candidate. And so basically, like if you want to analyze the results, like usually I use this kind of plot, and then I try to find clusters of active molecules that are predicted like highly active. And we can also look at the distributions. It will probably not actually show anything here. So we can see that we were not really able to move the distribution. But I think for the more successful models, probably this histogram has a peak maybe closer to number 8, I think. Yeah. So like I think around 8, when you set the hyperparameters a bit better, you sort of hit a wall where you get a lot of molecules that are like close to 8, but no more than 8. Yeah. So when you look at the desirability ratio, it still tends to rise a little bit. Yeah. So yeah, it makes sense to run it maybe for like 1,000 epochs. Yeah. Yeah, and this is yeah, this is just comparison with the original. Yeah. So here we can see that we didn't actually do that well compared to the original. Yeah. Yeah. So yeah, that's it for the tutorial. We are actually right on time. 1 minute after 5:30. Yeah. So yeah, if you have any questions or feedback or whatever, just we can do it now or in the pub later. All right. Yeah. Thanks for the attention.
What else, Jerry?